Welcome to NeurIPS2020 Nairobi Meetup.
Hello, welcome everyone. Welcome to NeurIPS2020 Nairobi Meetup. We are really excited to have each and every one of you join in here today with us in this amazing meetup. As you are dialing in, please head over, settle back and let us know in the YouTube live chat where you're dialing in from. What are you most excited about today in this meetup, and what are you hoping to learn new today? We are really excited and really grateful for our amazing panel of speakers joining in today to have a variety of machine learning research and application presentations and sessions. We are really thankful for them to take their time to share their professional experience, knowledge, and practical experience that they've gained over the years in a variety of machine learning subdomains and expertise. Thank you so much to our amazing group of speakers for joining with us today. Thank you so much. We're also really excited for having a Women Shaping the Future of AI workshop during the event, where our 4 female AI speakers will engage in a panelist discussion to share their opinions, perspective, and have a discussion during that workshop, AI workshop. A little bit of background on NeurIPS. Neural Information Processing System is an annual machine learning conference that is organized and hosted in various locations every December in the US, Canada, or Mexico, where the main purpose of the conference is to foster the exchange of machine learning research on various technological, mathematical, and computer science aspects. The conference critically focuses on the presentations and talks on peer-reviewed novel research papers, which are presented and discussed by some of the smartest minds in the industry. The main conference this year is being held completely online. A little piece on NeurIPS meetups. As we are joining today, this is NeurIPS meetup as well, which are local events hosted during the NeurIPS conference at the same time during December that leverage the scientific content of NeurIPS, as well as live local content from AI researchers and practitioners that last ranging from a few hours to sometimes a full week. These events bring together participants from companies, universities, and the public as well. These meetups were debuted last year in 2019, where 75 meetups were hosted in 35 countries over 6 continents. This year, we have 9 countries in Africa alone in 2020, where similar meetups are taking place. All of these meetups are governed by the NeurIPS Code of Conduct. This event, Pi and AI Nairobi 2020 NeurIPS Meetup, is in collaboration with the Pi and AI Nairobi, as well as the Pi and AI Chennai committees, in collaboration with Google and NeurIPS itself. Pi and AI are a series of deep learning AI meetups that are independently hosted by the global AI community in various cities around the world. These events include conversations with AI leaders, thought-provoking discussions and engagements about the latest trends in machine learning, where the AI space is heading towards as we go into the future, as well as what are the best practices, tools, and tips to get started in machine learning research and practice. During these meetups, our learners and our attendees get to take advantage of the amazing content that we share with our speakers, as well as get to network with each other and learn from each other. So we hope that going forward from today's meetup, you will talk to each other and even get started on research topics or projects with each other. A little bit of what we have been able to do so far in the Pi and AI Nairobi Deep Learning AI community. We have been able to recruit and motivate over 300 deep learners in Kenya, Rwanda, and India as well. We've had a successful track record of hosting 9 physical as well as online events in this past year that have been highly impactful and have attracted a large number of attendees that have joined all over the world. We've also been able to negotiate valuable partnerships and collaboration with companies, universities, and organizations And we've been able to introduce our attendees to the amazing content that deep learning AI has to offer. Just this September, we've hosted an event in collaboration with the Alan Turing Institute. The organizing team today that made this entire meetup possible are Kennedy Wangari, Raman Sharma, Griven Ochieng, Manpreet Budraja, Nicholas Mosau, Jean Nyondi, and our amazing team of volunteers, Billy, Rosanna, and Sanmitra. We are really thankful to our entire team for organizing this event from the start to the end today. So what should you expect from today's meetup? You should expect to learn about new cutting-edge technologies, advancements, and trends and tools that developers, engineers, and researchers use in machine learning research and application. You'll have an opportunity to learn and have an interactive session with our amazing speakers that we have invited over here today. You'll get to learn from their experience and knowledge in academia and industry. You'll also have a chance to engage with NeurIPS scientific content, where you'll get to explore research papers, interesting tutorials, workshops, and presentations streamed during the actual main conference. Of course, you'll also get to meet and network with like-minded people joining in from around the world today, and see where you can take this networking style further by collaborating on projects and further ideas. Today, our Q&A platform will be held on the Slido platform. So if you have any questions at all during any of the presentations, please head over to slido.com/NIPS2020 to ask your questions, and we'll do our best to ask your questions to our speakers during the Q&A sessions that we'll have. So please take note of this link. It will also be shared in the live chat throughout the event by our volunteers. If you would like to tag us in any of your social media posts, the hashtags for today's event are #NeurIPS, #NeurIPS2020, #NeurIPS Meetups, and #NeurIPS Nairobi 2020. With that, I would like to welcome all of the attendees that are joining today and our speakers once again before we get started with our first session. So without any further ado, I would like to welcome our first speaker for today, Andreas Damianou. He's a senior scientist at Amazon working on machine learning and information retrieval. Before Amazon, Andreas co-founded Inferentia and was a machine learning researcher there until the startup was acquired by Amazon. He has also been a research intern at Microsoft in the past and a research associate at the University of Sheffield, where he worked on machine learning and social robotics. Before that, he has also pursued a PhD degree with deep Gaussian processes and variational propagation of uncertainty. He has an extensive experience having worked in a variety of application areas, such as multimodal information fusion, decision-making, information retrieval, and AI-assisted data science. He has also published a research paper at ICLR in January 2020 on empirical-based transductive meta-learning with synthetic gradients. A fun fact about Andreas, he celebrates a selfie moment with the Queen of England herself. So thank you so much for joining us, Andreas. I will now let you share your screen to start your presentation.
Great. Hi everyone. First, let me just check. You can hear me well?
Yes, thank you. We can
perfect.
Hear you well.
Let me just share the screen. And okay. So hopefully now you can see my screen. It's just the presentation title.
It's visible, yes.
Perfect. Okay, so I can start. Just the last question. So as we agreed, I have 30 minutes of presentation material, and I can take questions in the end. Is that correct?
That is correct, yes.
Perfect. Okay, so thanks for the invitation. I'm very excited to be here. Actually, I'm happy to be in Nairobi virtually. I have been there in 2015, so kind of coming back after 5 years virtually this time. Thanks to the organizers for inviting me. It's really an honor to speak in this meetup and to meet all of you and interact with all of you. It has been really nice so far, the organization, so thanks so much to everyone. Thanks for the nice introduction as well. And I'm just going to now start my presentation, and please feel free to note your questions and the slide number if you want to discuss them later. So this talk is about deep learning in the function space. And I made the talk in a way that hopefully you can follow even if you don't know that much about deep learning even, or about the Gaussian process aspects I'm going to discuss. So hopefully you will be able to follow. So deep learning is a very popular domain, and usually people create deep neural networks and they treat them as functions. So let me start with this sketch here just to motivate what I'm going to be talking about today. So a deep neural network is a function with many parameters. This sketch here is how people typically show deep neural networks. So you have some inputs, let's say some images, and then these inputs are passed into layers that are governed by weights, multiple layers, and then you get the output. For example, 1 if the image contains a cat, 0 if not, or whatever. And we'd like to treat it as a function and say that the output is a function of the input, obviously, and the parameters. And the parameters have to be trained. Now, deep neural networks have a lot of parameters and a lot of layers. And the question here is, what is the connection between parameters and the properties of the induced function? And what about architectures? What about skip connections? What do they do? How all these things affect the function? Why do we care so much about the function? Because it's the thing that we use to make the predictions and to argue about our predictions as well. For example, there is this paper called the lottery ticket hypothesis, where the authors talk about different subnetworks inside the big deep neural network. So the question here is, should we think of those as sub-functions? Let's call them phi. And if yes, wouldn't it be great if we could characterize and therefore study the constituent subfunctions within F? If we could say, for example, that my function F, which is the big neural network, really is a composition of, the red phi and the green phi and the blue phi subfunctions. It would be nice if we could do that, because then we could create deep neural networks somehow like Legos. We could just piece together appropriate phis and appropriate subfunctions and create kind of the structure that we wish, instead of having to, cram all the parameters together, optimize them, and hope that something comes out. One motivation why we should care about functions. Another motivation, what about removing a node? So before I talk about function F with parameters W, what if I remove this node here and the associated parameters W? Then I should get a new function, which I call F prime. Now, what is this function? We don't know, right? We should know, though. That's my argument, because that's how compression works, for example. We can delete some nodes to compress a network, or even dropout or regularization. So it could be really nice if we know what are how can we associate changes in the parameters with changes in the induced function. And this goes beyond structure. It's not only about structure. Here I have identical structures, identical weights and everything, identical weight structures and everything. But here I have a network that I have been training for, let's say, 5 epochs, and here's a network that I trained for 90 epochs. And obviously, I should say that this is a different induced function, right? Again, why should the function that I care about be depending on a discrete number that I have to select, which is here is the epochs or the optimization steps? Wouldn't it be nice if we could start arguing about functions as mathematical objects instead of having to depend on all these things? And the last motivation is this in transfer learning. So transfer learning is very popular, and it's one of the de facto ways of using deep neural networks, basically. So here I have the blue network, depending on some parameters, W blue, and then the red network, depending on some parameters, W red. And then I somehow do this kind of transfusion where I take one of the blue layers and I put them as part of the red network. So what does that mean, right? I mean, now this network here has the parameters of the red parameters and the blue parameters, but unfortunately, we don't know exactly what we have transferred, right? We don't know exactly what we transferred in the first place, because we cannot characterize the layer that we transfer mathematically as a function. It's just a bunch of nodes, which we have some intuition about what it's doing. And then after we transfer, we also do typically fine-tuning, meaning that we take a few gradient optimization steps. And this is for an arbitrary number of steps. So again, we don't know how to characterize the result after all this. So this is just my motivation slides. And what I want to say here today is, why shouldn't we just cut the middleman and deal with functions directly? So if we were able to do deep learning over functions, then we would move from this situation, which is what I showed before, which is, you have a function that depends on different sets of weights. We really don't know how these weights interact. It would go to this situation here where you say, have function 1, function 2, and I compose them, and there is mathematical ways to express the composition because we know how to compose functions. So that's what we would want to do. It's more intuitive, but also it's more practical in certain situations because we can also encode our prior knowledge and assumptions. So you can say, for example, that you have a classifier that predicts, 2 classes, and somehow your prior assumptions is that this function should a priori at least equally predict class 1 or class 0. You can put that as a prior in the function itself easily. But if this classifier has a lot of parameters, then what is the prior on these parameters that you should put so that you get the induced properties that you want later on? That's not clear. So that's why we would want to work on the function space. So hopefully I have convinced you, at least motivation-wise, why it's good to think on the space of functions. And the first results of how we can connect deep learning to functions comes some time ago from Neil 94 and then Williams 97, about how neural networks at initialization and at the infinite width limit, meaning if you take infinite number of nodes, converge to Gaussian process. What this means is that if you have a neural network and you have these nodes to be infinite in size, then instead of having to optimize all this finite number of parameters associated with these nodes, now you just get a closed form function characterization, which is a Gaussian process that involves some integration. So optimization of finite parameters becomes integration of an infinite model. So it's infinite model, but integration means that because if we know integration formulas, it can become closed form and characterized mathematically. So this is really cool. And surprisingly, long ago, after this first result, a couple of years ago, this argument has been extended to multiple layers as well. So even for multiple layers, in the same limit and some mild assumptions, that you get a Gaussian process out of an infinite deep neural network. I'm going to discuss about the details, but it's not very hard to imagine how. It's basically by invoking the central limit theorem. I haven't even studied what's a Gaussian process, but at this point, it's just important to remember the Gaussian process is basically a prior over functions. It's a way about arguing probabilistically over functions, and ultimately, it's a kernel machine. So a kernel machine is doing inference based on similarity. I'm going to discuss about this in a bit, but this equivalence is not that surprising. Basically, it says that somehow a neural network memorizes the inputs through its parameters, and it mimics similarity-based learning as expected, basically. And indeed, the kernel machine is equivalent to a dot product in the kernel space, right? So it's not really that surprising. I saw someone turn on their video. I don't know if that was because of a question or it was a mistake. Is there like something, if someone is like really left behind, I would be even happy to ask a quick question now.
I think everything is going fine.
Okay, perfect. Thanks for the confirmation. So this equivalence that has been studied at initialization, when you initialize neural network, how it converges to Gaussian process. So let me just now drill into that a little bit more. So what is a kernel machine or a Gaussian process? Just a schematic. You can see more in my tutorial that I have the link here. So imagine that you have a function. It's this kind of sinusoidal form. You don't know the function. You just have some, let's say, training data, which is these orange dots. And then you have a query point, which is this green cross. And you want to do similarity-based learning. So what similarity is? So in the kernel space, in the kernel world, it means that you have the kernel itself that is telling you what similar is. And so in the kernel space, if you have a radial basis function kernel, the most similar points in the kernel space would be the immediate neighbors to this one. So it means that the ones that have the most, the biggest, let's say, covariance with these points are these ones. But this is just because we select a kernel that encourages smoothness. If you get a cosine kernel, that is a kernel that takes into account frequencies, then you see that the closest point to this green one here is not the immediate neighbors, but is this far away couple of points here, and then this far away couple of points here. Why? Because they are in the same part of the frequency circle cycle as this point here, because you see it's like after one period and then after a further period. So what similar is defined by the kernel. And this is actually really powerful because we can say what similarity is. Do we want to encode frequencies, periodicities? Do we want to encode only smoothness assumptions? Do we want to encode trends? All these things. And they're going to do inference then for a new point, x star. So let's say that actually this green point you have never seen before. It's one that we want to infer the y value, the output value of that of the function. So they want to do with a kernel machine is simply by taking all the training outputs y and take a linear combination of those. So that's why it's a similarity-based inference. So the output for the y value for this green guy here is going to be just a linear combination of all the other y outputs for the orange points. But it's a weighted linear combination. And the weight is going to be proportional to the similarity of the output values of these ones. That's what this kernel here says, basically. And the similarity notion itself is governed by the kernel. Okay? So that's how the kernel works. And in a bit, I'm going to discuss about how can we have kernels that are data-driven and neural network-based. So you learn the similarity, but we'll get there in a bit. But before that, I'm going to make the philosophical question, which actually, again, David Mackay made. Have we thrown the baby out with the bathwater? What does it mean? So, okay, I want to get rid of the optimization in the parameter space. We like to talk about functions. But wait a minute. We know that deep neural networks partially work exactly because we use SGD, which is doing this hierarchical feature learning, So instead of learning the whole function together, first you learn one layer, then you learn another layer, and this helps to decompose the concept into sub-concepts and learn it better. So in this case, the baby that we throw with the bathwater would be the hierarchical feature learning, which is something that we want. So how have we actually done that? So people think about this, and actually, 30th of November in this year, there was a paper that said every model learned by graded descent is approximately a kernel machine. And then 6 days later, there was this Reddit post and paper that said neural networks are feature learners; they are not kernel machines. So which of the two is true, right? This come to seem like they contrast each other. And again, another quote by David Mackay that he had also kind of philosophized about that. He says, according to the hype of 1987, the previous hype, not today, neural networks were meant to be intelligent models that discovered features and patterns in data. Gaussian processes, in contrast, are smoothing devices. How can Gaussian processes possibly replace neural networks? Were neural networks overhyped, or have we underestimated the power of smoothing methods? I think both of these are true. So in light of recent developments, my proposition here is why cannot have both? And I promise it's not going to be all about memes. The rest of the presentation is just the last one. But why can we have both, right? So the kernel equivalence that this paper and also the ones I discussed show actually has a nuance. So wide neural networks are resulting data-dependent kernels. Somehow, this is the catch, right? It's not a traditional kernel. The kernel is adapted to the data in the same way that the neural network representation is adapted to the data as well. But still, it's a kernel, so it's still function space inference. So I think we could have both, right? Both learning features and doing inference in the kernel or in the function space. You can even think of it as, roughly speaking, as data-dependent kernel, which is kind of discovering functional features. So yeah, I think we can have both, and I'm going to show some part of my research as well that we try to do both. We want to learn rich features, like these hierarchical features that you see in deep neural networks, like edges or whatever, language properties if it's like BERT, but we want to argue in the function space. So here's the first step I'm going to show in the next slide, that we try to do that in my research as well. How can we use traditional deep neural network frameworks for optimization to leverage the feature learning, but then move to the function space when we want to do operations where function manipulation becomes interpretable in the function space. So here it goes. The idea is do that in transfer learning, for example. It's not the only application, but it's a good motivating story. So transfer learning basically says, okay, I said before that when you do transfer learning, it feels a bit arbitrary. How can we take a learned function and adapt it by just doing fine-tuning, or just by taking like the last layer and fine-tuning it, or the last 2 layers? These are all look arbitrary. What if we take a trained neural network, it has learned its features, we do it normally as we do, and then we package it inside the function. And now that it's packaged inside the function, we can say, I'm going to transfer to this situation by doing function operations, function inference. So that kind of feels like the best of both worlds, because I know what my network is a trained function, right? I know what prediction is doing, but then when I do the transfer, I know exactly what I transfer. I transfer the full network. And the way to transfer, as I'm going to show, is by doing a function operation. So no more fine-tuning, selecting layers. It's just a closed form. So that's what I'm showing here in the picture, and then I'm going to the bullet points above. You have a source task. Let's say you do you train a network to predict cats and dogs or whatever, right? And then your target task is prediction of I don't know koalas and kangaroos or whatever, right? So normally, so the contours here represent optimization landscape when you move in the weight space of this source network. So normally people take discrete steps in this optimization landscape, and they try, to navigate and reach this global optimum for the new task. But that's tricky. You don't know how many steps to do. You can get trapped in local optima. And what I'm suggesting here is, how can you basically teleport yourself right to the solution for the target task by doing function operations. And remember, function operations, they don't require this step optimization. Yes, there is a catch. To do that, you need to do some further assumption about actually not reaching the task that you want, but a linearized version of that. So it might not be exactly the solution that you want, but there is research from Lee et al. Sorry, I don't have that. I should actually have this references further. There is research that says that these two things should be close to each other: the linearization of the ideal task and the actual task when it comes to learning with neural networks. So that's what we want to do. And again, let me go now in more details about how we do that. So normal deep neural network learning on source data X, cats and dogs or whatever, we feed the parameters W. Now, second step, we encode the trained deep neural network function as a kernel. So now take the whole function of the deep neural network, not the last layer, not the one before the last layer, but take the trained deep neural network. Again, not the one at initialization as previous research that I discussed, the trained one, and you encapsulate it inside the kernel, which I'm going to explain, which I call K deep neural network. And now, since I encode it in the kernel, when I have new inputs, for example, from a new domain, I can predict with a Gaussian process that has this kernel. So now my prediction happens in the function space. And not only that, but because Gaussian process is a Bayesian model, now what I have done is I cast transfer learning as Bayesian inference, basically. The prior distribution comes in the form of the source task. It encodes all the features that we hope are common among tasks. So that's my prior information, things that I have learned that I think are good for next tasks. And then when I do posterior learning, the updates of the posterior update the beliefs by seeing data in the target task. So I see some images of, let's say, kangaroos and koalas, and update my posterior inference about how the function should distinguish between the two, but without forgetting about the source task that was, let's say, cats and dogs, right? I don't forget, this is my prior in terms of how images behave in the similarity space. So that's the idea here. And just to show this a little bit more clearly, what is a form of this kernel? This comes from the neural tangent kernel, a family of approaches that you might have heard. Is quite popular recently. This is the initial paper. There's a few others as well, and this is our paper that explores that for this transfer learning scenario. So this neural tangent kernel takes this form. In our case, it's a neural tangent kernel at convergence, so that's the difference. And it's a kernel that's governing the gradient descent dynamics around convergence. So basically, the theory here is that this is an equivalent kernel that if you were doing learning in this kernel space, you would find the same solution with a deep neural network. Now, in practice, people have tried to use directly this kernel, and they don't get as good results. And I hypothesize, and I think other people have hypothesized, this is because if you use just the kernel, you cannot do this feature learning that SGD is giving you. So we try to kind of bring the best of both worlds. We do learn the neural network traditionally, and we just invoke this kernel for transfer learning only. To do the transfer learning in the function space, which is very data efficient, as I'm going to show, more intuitive. It's closed form for regression, and that is not depending on this local minima. Just to dive a bit into this kernel basically, J here is the Jacobian of the deep neural network. So the kernel, of course, is a function of the inputs and the parameters of the deep neural network. So it's basically the transfer of the Jacobian with respect to any input and with respect to the trained parameters, transpose that times the same. So for a new data point or for any input, to compute this kernel, I just have to compute the Jacobian of the trained network. The Jacobian of the trained network is going to say what similarity is for the inputs. So if I have now inputs in a new domain, it's still useful to have this kernel because it's telling me, okay, that's a new domain. It's koalas and what they say, kangaroos or whatever. It's a new domain, but my kernel has already learned a different domain what similarity between images of animals mean. So it's useful to use that as inductive bias. So that's what this approach is doing. It's using a trained neural network in one domain as inductive bias for a target domain. Okay, so let me show some results for that. Here it's a small example where it's actually a prediction of malaria cases in Africa. And we have split the task into the source task and to the target task. So the source task is a measurement of cases in some time in the past, and the target task is measurement of cases in the much more recent past. So there is two issues here. One is that there is a slight distribution shift across time. So in the target task, things have changed. So what we want to do, we want to see how we can build a deep neural network predictor on the source task that has a lot of data, that knows how to do the prediction in this historical data. And I say, okay, now we have a distribution shift, we have new data, and we do measurements now in hospitals, and we have very few data. How can we leverage these measurements and also leverage the knowledge we have from the model we built on the previous measurements from the historical data? So the x-axis here shows the number of adaptation points, meaning new measurements, new cases of malaria, for example. The more you have, the better you can learn to predict in the present, obviously, right? But these are never going to be enough because ultimately it's very few data. So if you don't use fine-tuning, you just train in the past, and then of course you ignore any recent data. So it's the purple curve. It doesn't change as you add more points because you just ignore them. If you do fine-tuning, you get a smaller error in the y-axis compared to ground truth, but the difference is tiny. And the reason is because these points, the new task, are not enough, just because neural networks need a lot of points to learn. But with our approach, which we term finite NTK, by the way, here is the repo if you want to see a lot of cool transfer learning approaches, including this. Yeah, with our approach, you can very efficiently use these new points. So even with like less than 100, you can already take them into account well without forgetting what you learned from the past cases, from the source task. And the more you see, the more you can reduce the error. And this is because we do now inference, as I said before, in the function space. So we package what we learn from the historical data as a source task, and then we just do data efficient update of our posterior belief when you see new data in the function space. No local optima, none of these issues. So that's how this works. That's almost the end of my talk. I discussed about how we can leverage both feature learning and function space inference, and that these two things could be made compatible. But before I conclude, I want to show a little bit of another part of the research that I have done, which also is along these lines. We switch gears now. So that's a different family of approaches. It's deep Gaussian processes. It's basically what came out of my PhD, and now it's an area of research that quite a few people are practicing. So the intuition here is that you want to do hierarchical feature learning, right? And you do it just directly in the function space. So, okay, if you just take a Gaussian process, a single Gaussian process, yes, it's true that maybe you cannot learn hierarchical features because you learn the full functions at once. You cannot leverage from this decomposition of concepts into hierarchies. Okay, why not stack Gaussian processes and then learn functions hierarchically? So that's what we did in these papers. And you can see how this works. So imagine that you want to model this sort of functions here. They're very funky, right? So you see that this family of functions is smooth, and then it becomes very rough, and then smooth again, then rough again. It has some symmetries, like here there is symmetry, here there is symmetry, here there's symmetry. How can you learn all these different properties across the x-axis? Well, if you decompose the function, this becomes trivial. So your input is just 1, 2, 3, 4, 5, blah, blah, blah. And then all you have to do is warp your input through this function here, which is simple. And this allows you to decompose all these nuances here. Because look, when this function is changing rapidly, then the next layer becomes very rough. When this function is not changing, this function becomes very smooth. Furthermore, this function is encoding our similarities and our correlations, right? So it says that basically this area and this area should be the same. So that's what's happening here, right? So the symmetry here and here is just encoded by this function, intermediate function. Same with the symmetry around here and here. It's encoded here, right? So basically, to do that, you have a Gaussian process mapping that is fed into another Gaussian process mapping, and you have to learn both Gaussian processes. Okay, and that's not a trivial thing to do. I mean, there's a lot of approximations how to achieve that, but you can check the papers if you want. I also have the same tutorial about GPs that I showed before. So I have just one. Now I say the organizers appearing because it's almost at the end. I have just the conclusion. I have time for that, right?
Yes, I think we can conclude as well, yes.
Okay, so it's basically just this slide here. Thanks for your attention. More transfer learning stuff in this link. Just to conclude very quickly, I talk about how hierarchical constant learning manifests in DNNs and learns well for large data, but function space modeling is desirable because it's interpretable, avoids local minima, and is data efficient. And I argue that, if we are a bit clever, we can actually combine both. And I show that how this can happen if you consider the kernel limit of the trained DNNs. And in the last slide before, I showed that we could even do hierarchical learning on the function space directly. That's all from me. Thank you so much. I'm happy to take questions now.
Thank you so much, Andreas. I will, if you can stop sharing your screen, I will now share our Slido platform to ask the questions we have received from the attendees. Thank you so much. So thank you so much for that amazing presentation. It was highly informative and mathematically rigorous. We all had a lot to learn from it. Thank you. I think we can ask this question. So it's a bit, so you founded Inferentia sometime earlier, right? So what advice would you have to give someone who wishes to blend machine learning research and entrepreneurship at the same time, if they can?
Yeah, thanks for the question. That's a good question. It's always tricky because machine learning research is often about the state of the art. Entrepreneurship is about making things work. So I think it's useful to keep this in mind. I know it sounds trivial, but I think it's just easy to forget, especially if there is a lot of hype. Making things work when it comes to entrepreneurship doesn't mean necessarily, emphasizing new method, because the existing methods we have, we don't understand them very well. So revealing nuances and problems in existing methods, that's actually, in my opinion, how you can push the state of the art when it comes to entrepreneurship and how to actually create things that work, but at the same time are novel and desired, right? So look at what we have and try to understand them and understand what are the caveats and why they don't work. So deep understanding for me, I think, is important. And other than that, also not go, I guess, in the other end in an apprenticeship, meaning that you forget to keep yourself updated about what is happening, right? I think it's always very useful to keep yourself up to date about what's happening in the world and be ready to pivot if something comes up that is changing slightly your entrepreneurial directions.
That's okay. That was really true. You need to be able to be flexible, especially with regards to the entrepreneurship part of this blend. So thank you so much, Andreas, for that amazing and informative session, as well as answering this question. I would like to remind our attendees to use this link to keep asking your questions. And now I will welcome our next moderator, Griven, to start the session for the next speaker. So Griven, please. Griven, you are muted, I think, right now.
Thank you so much, Ramesh. Sorry for that technical hitch. I think I'll go ahead.
Yes.
And so next on deck, we have Jiayu. Jiayu is an AI research intern at NVIDIA with 1 year of experience in research and development. He previously served as a research assistant and a research intern at the Technical University of Munich, and has also previously served as a data engineer at Baidu and a part-time software engineer at Altair. Jiayu is not quite familiar with Slavik's last names, though he finds them to be as cool as the names of neural networks. And so today, Jiayu will be taking us a talk on active learning with neural networks. Jiayu, if you can hear me from the other end of the call, say Jambo.
Jambo.
Well, think then you can go ahead and share your screen right now.
Yeah, thanks for the introduction. Let me just quickly share my screen. Is my voice clear?
Yes, it is.
Yeah, all right. Thanks. Thanks for everyone for coming. My name is Jiayu. So today I'm going to talk a little bit about active learning and how we do active learning with neural networks. And the contents of this talk is partly based on the results with the joint work with Johannes, Rudolf, and Daniels at the Technical University of Munich. And yeah, so today I'm going to talk about active learning. So what is active learning? Before introducing what is active learning, so let's take a look at what is happening in the standard supervised setting. So in the standard supervised learning, the basic pipelines for us to learn a classifier is that we collect some data, and then we label those data, and then we feed those data to a learning algorithm. And finally, the learning algorithm will output a trained classifier. So the pipeline here is that we always have a sampling step. So we sample some unlabeled data from the unknown distribution Px, which is assumed to be IID. And this pipeline can be think of as passive because your learning algorithm has no control over which data to observe because the labeled data are always given. Oh, by the way, here, the oracle is always meant to be, for example, a human labeler or an expert that can give you a correct label of your unlabeled data. So in contrast to this standard supervised learning, which is in some sense passive, active learning, in active learning, the learning algorithm play a more important role. So the learning algorithm have more freedom to select what data it will observe. So if you also sample some data from the unknown distribution, but instead of labeling all of them, the learning algorithm has the freedom to choose a subset of them to be sampled. For example, the learning algorithm may think that the xj may be interesting, and they will query the xj for its label yj. And once the label is queried, this label sample will be added to the training set, and the learning algorithm will kind of train a classifier. And depending on the quality of the classifier, the learning algorithm can still query more labels. So the protocol here for active learning is that the learning algorithm can query and train. And this kind of query train round is the core protocol of active learning. So people might ask, why do we bother whether allowing additional freedom for the learning algorithm to select data? The main goal of active learning is that we want to train the same classifier using as few labels as possible. So this is the main objective for active learning. And this is turned out to be quite essential because in many applications, label data is quite scarce or they are quite expensive to obtain. For example, in autonomous driving, which is what we do in NVIDIA, it may be quite easy to collect like thousands of frames of driving scene without any high cost, but getting them labeled by some human labelers take a huge effort. So the typical setting in here is that in the company or in the industry, we always have a fixed budget for labeling. So we always want to train the best object detector using as few labels as possible. So this is the motivation for doing active learning. And this is also one of the main tasks for active learning. So before I introduce more into the topic, so let's see an experiment example and understand what is the problem and what we can hope for the best for active learning. And let's take a look at this inspiring example. So in this task, we want to learn some 1D data that is in the real line. And in this specific example, our data X is distributed uniformly between 0 and 1. And we also further assume that they are separable by some unknown threshold function. So here we denote that target function as H star, and it has some threshold T, which is unknown here. And the goal of this learning task is that we want to learn the classifier H, whose error rate is at most epsilon. So the question I want to ask is that how much label do we need to achieve this goal? And it turns out that we roughly need 1 over epsilon labeled. And why is the case? Because if you sample uniformly 1 over epsilon samples with high probability, the distance between adjacent points will be roughly epsilon. And once you have this data, you can just fit a threshold function to here. And you are guaranteed that with high probability that the learned classifier has error rate at most epsilon. And I want to show you that in this inspiring example, active learning can do much more better. So the idea is that we can apply a binary search. So what we do here is that we still sample 1/epsilon samples, but we keep their labels hidden. And then we apply the binary search. So we query the label of the point that is most near to the center, sorry. And once it's labeled 0, for example, in this case, it's review. And then we know which subinterval is the unknown threshold located in. And then we can move forward to the next binary search. And by following this procedure, it can be shown that we only need log of Damianou needed by the passive learning, which is log 1/epsilon labels, which is quite impressive because we achieve a huge label improvement in terms of a number of labels that we needed. And the core idea of this active learning is that we perform an efficient search through hypothesis space. And I just want to talk more about the label efficiency of active learning. So in general, for a VC class of VC dimension D, and for separate data, the passive learning label complexity is roughly D/epsilon. But for active learning, in general, it can be guaranteed that an exponential improvement can be achieved. In this case, for active learning, the label complexity is roughly theta D times log 1/epsilon. So you can compare this two formula here, although they're asymptotic, but they do show that in general, in the minimax sense, the number of labels needed by active learning is much less than passive learning. And there might be some question about the non-separate data. So what will happen in the non-separate case? In today's talk, I'm not going to talk about too many details about non-separate case, but the answer is that for non-separate case, this exponential achievement is not possible in general. And what I want to talk about today is that how do we implement a search in a general hypothesis space? And especially how do we implement this idea in the space of neural networks? Because neural network is kind of the state-of-the-art devices to do all kind of prediction tasks. And it would be really helpful if we can extend the active learning method to neural network to see how much benefit can we obtain from using active learning method on neural networks. So one idea to apply this search is that we can do an aggressive version space reduction. So let's talk about what is version space. So assume that we have a hypothesis space, which is the set of hypotheses. We denote it as H, and the prior called pi. So the version space V here is denoted as the set of hypotheses that are consistent with our set of query label samples, which is denoted Q here. So you can imagine the V as all the classifiers that fit your training data. For example, if you use neural networks and assume that your training set contains 100 label images, and the version space is the set of all possible neural networks that you can get from training on this 100 label images. And all those neural networks kind of consist this version space. And to apply this, to generalize the binary search idea to a general function space, one idea is that we do prior mass reductions. So let's just ignore this formula here if you think it's too complicated. You can just focus on the right-hand side diagram here. So it may be easier to understand. So the version space is depicted by this irregular shape here. And there are all the hypotheses that are consistent with our training data. And for example, if we are interested in query xi, and in the binary case, the label of xi is either 0 or 1. So we can partition our version space into halves. So one halves that are consistent with xi being labeled 0, and the other half consistent with xi being labeled 1. So once the label of xi is revealed, our version space is split. And this is quite similar to what happened in the binary search case. But instead, this works in general for a general function space. So in prior mass reduction, we want to select the X such that in the average case or in the worst case, the most part of your prior mass is removed. And in this case, assume that the true label of Xi is 1. Then this shaded area here, denoted by this blue shaded here area, will be removed. And the idea of prior mass reduction is that we see the X such that the maximum shaded area can be removed. So this is what we generate the binary search to a general function space. But it turns out that this prior mass reduction is problematic because it might happen that even though the prior mass of your version space is substantially reduced, it could also happen that the hypothesis in your remaining version space will still have a large error rate. So by error rate, I think it would be beneficial if we define a distance metric for functions in the version space. So we define the distance between a pair of hypotheses, D, H, and H prime, as the proportion of X that they disagree with. And this distance metric is quite useful because it gives you the error rate once you plug in one of the hypotheses with the ground truth. For example, if we think the H prime give you the ground truth, then the distance between H and the ground truth is the probability that H classified wrongly with respect to the ground truth. And this probability is actually the error rate. So in prior mass reduction, it can happen that your version space mass is substantially removed, but the distance between hypotheses is quite large. And it's also possible, therefore, that your hypothesis will still have a large error rate. So the correct way to do version space reduction is to do diameter reduction. So let's focus on the bottom left and right diagram here. So what we query is that we want to query the X such that when its label Y is revealed, the remaining subspace has the minimum diameter. Or in other words, the remaining version space, in the remaining version space, the hypotheses are close to each other. So that in the worst case, we can guarantee that the worst case error rate is minimum. And this is the correct way to do version space reduction, especially for classification. And so it depends, depending on what kind of diameter measure we use, there might be several variants of this version space reduction method based on diameter reduction. So one diameter measure is the pairwise disagreement. So we measure the diameter of our version space by the expected distance between a randomly drawn pair of hypotheses. Another diameter measure, which is what we propose in our paper, is that we take the average distance between a randomly drawn hypothesis to the majority vote hypothesis in the version space. And it turns out that these two diameter measures are closely related. And we just show that they like sandwich each other by a factor of 2. So with these tools at hand, we can do diameter reduction for neural networks. But before showing you the results, let's talk about a serious problem that plague many active learning heuristics. There are just basically 2 problems. One is the sampling bias, another is called inconsistent problems. So the sampling bias says that in active learning, the data we use for train our classifier is not IID. So in the standard statistical learning setting, we cannot like derive any results that is like sound and guarantee that we can achieve some optimal error rate because our data is not IID. So also like associated with this sampling bias problem is the inconsistent problem. That is, once our data is not assumed to be IID, we are not guaranteed that as more label is queried, we are guaranteed to find the optimal hypothesis at the end. And I just want to show you a counter example. So why this sampling bias and inconsistent problem really matters. And this example is given by Dasgupta. It's quite interesting here. So we are back to the learning threshold function toy example here. But instead of having a uniform distribution, our data X is distributed in some clusters. So in particular, there are some two large clusters here. One large cluster near the end of the interval, and another large cluster here. And if you want to do active learning on this data set, we first reassemble some data. So we will end up quite likely that most of our training data will from the left and the right large cluster. And if we don't care about the sampling bias, it is likely that we will always query in the middle of the interval. For example, if you use any heuristic like uncertainty-based or margin-based sampling scheme, then we will probably end up query in the middle of this interval here. And it turns out that the hypothesis that we obtain here, which is h hat here, has an array 2 epsilon. And I just want to say that this array is not the optimal array that we can achieve from this toy example. The best array we can achieve is epsilon actually, through this h star hat here. So you can see that the h hat misclassified this two small cluster here. So its array is roughly 2 epsilon, but this h star hat only misclassified this blue small cluster here. And its array is epsilon. So by showing you this toy example, I just want to mention that we always want to care about the underlying assumption of the data distribution and the hypothesis base. And we always need to use a sound method that is guaranteed to be consistent for active learning. And one way to guarantee the consistency is that is using version space reduction. But there's one condition for version space reduction to work. That is that the version space always contains the ground truth. In other words, the ground truth classifier is always contained in your hypothesis space. And this is the conditions for the version space reduction method to work. So before showing you the evaluation result, I just want to quickly examine whether the data is separable by the neural networks in general for a variety of image classification data sets. So what we do here is that we project the ground truth to our version space. So the ground truth here is denoted as the H star. And we project this H star to our version space V or V tutor. And we obtain a projection, H projection, H star. We just examine the distance between the ground truth and the projections and to see how large is this distance. If this distance is quite large, then it means that the version space does not contain the ground truth, and which means that the data is not separable. And what we do is that on 4 image classification data set, we construct a small random subset. For example, on MNIST, the whole data set consisted of 45K roughly images, and we construct a small random subset incrementally of size 400. So what we do is that we query 10 labels and another 10 until 400 for MNIST. And we plot the Ron agreement, which is the distance between the ground truth and its projections, as more data are queried, which is our show in these 4 curves here. And you can see here, although the distance is quite small, some number between 5% or 10%, but in general, the distance is not negligible, which means that in general, for neural networks, the realizability assumption does not hold. Or in other words, in general, on this 4 image classification data sets, the data, your images is not separable by your neural networks that is used. So this result turns out to be quite doomed, right? Because the only sound method that we use for active learning, which is the version space reductions, is not guaranteed to work because the core condition behind it is violated. But one comment from our experiment is that for neural networks, this turns out to be a tiny issue. So the conclusion is that version space reduction can still work, and it performs much better than random. Although there are some subtlety here regarding the reliability assumption. So let me just quickly show you the evaluation results for the setup. So in the evaluation experiment that we did, we compared 3 groups of methods. So the first group is the prime mass reduction, and the second group is the diameter reduction. And the third group is some other state-of-art like heuristic or baselines, including random. And what we shown here is that diameter reduction, which is shown in the lower block of these 3 methods here, outperform all the other methods, including random, which is shown in the first block, and the prime mass reduction, which is shown in the second block, and all the other baseline, which is shown in the third block. And so this is the test accuracy plots here. I'm not sure how much time do you have? Yeah,
we
so
still have
basically
around 6 minutes. Yeah, please go on.
Yeah. Excuse me for showing a small figure here, but because we are comparing too many different methods, so we just put an all there. So basically, what you want to see is that this green and this purple curve, which correspond to diameter reductions, and they outperform all the other methods. The random is shown in deep blue color here, and as you can see that on MNIST and Fashion and Street View and also STL, the green and the purple curve lies well above the random curve, and also above all the other strong baselines. And one interesting observation is that for neural networks, although an exponential improvement is not possible, it is still possible to save a lot of budgets to learn image classification tasks. For example, on MNIST, you can imagine that you can use just 100 to 200 labels to find a really good classifier. And another observation from this graph is that on some specific data set, the prime mass reduction method does not work always. For example, on this preview house number data set, the prime mass reduction method, which is the method that mimic the binary search in general, depicted in this red and pink curve here, it's quite worse, and it does not catch up with all the other methods at the end. And here I show you the diameter of the version space. And also it's a little bit messy here, but the key idea here is that the rank of the reduction in the version space diameter roughly correspond to the accuracy in the previous plot there. Let me just show you lastly a final demonstration, I think, which is quite intuitive, and show you how active learning for version space works. So here we plot the embedding of our neural networks from the version space. So for example, you see a large cluster here, and there are like roughly 20 neural networks here. And we just plot their distance and connect them with lines. And the purple cluster here correspond to the version space at the very beginning when you have only just 10 labels. And then we show a version space with more labels, for example, 100 labels, which is shown in this blue cluster, and 100 labels with the green cluster, and gradually to the red cluster, which is finally having 400 labels. And the ground truth classifier is denoted as this star here. So this diagram shows you that active learning actually works by reducing the version space. So as more data are queried, you can see that the diameter of your cluster shrinks quite much. And as we point out that the reliability assumption doesn't hold in general, so the ground truth classifier is not contained in your version space, although the distance between the ground truth to the version space reduces as more data are queried. All right, so let's go to the conclusions. And so there are just two observations from our study. So the first one is that diameter reduction methods are more effective than prior mass reduction. And the second observation is that some other strong heuristic methods are not consistently better than random. There are also some unsolved problems. For example, the first one is that the reduction of the version bit bias is not directly controllable. So, which is a really interesting topic in the future. And the second unsolved problem is that the prior mass induced by SGD may not be a reliable surrogate measure. So it might be some interesting work in the future to investigate these two unsolved problems. And I hope everyone can learn from my talks today. And thank you for your attention. And if you have any questions, just ping me. Thanks.
Well, thank you so much, Jiayu, for treating us to the gems of active learning in neural networks. So I'll pass it over to Ramesh, who will then forward questions from the audience. So you probably could stop sharing so that you can pop up questions.
Yes, thank you so much, Jiayu. We are getting a lot of amazing questions from our attendees all over. I think we can ask this one. So thank you so much for your highly informative session. This question says, how would you recommend a person, to get started in rigorous machine learning mathematics to not only understand and replicate research papers, but also to think forward and find something new to research on and understand?
Yeah, I'm not sure I'm well qualified to answer this question because I'm not experienced as all the other speakers maybe. But I think that if you want to start with the more mathematic domain of machine learning instead of the practical or application side, it may be better to focus more on statistics, optimization, and also it would also be quite interesting to study signal processing or information theory. And so they are all connected. And other than that, I think it would be beneficial to just start with a small topic that you think is interesting, and not just following all the others. For example, many people do deep learning architecture optimization or something like that. You can start with your own backgrounds. For example, if you are from a signal processing background, you may find some problems in signal processing that is quite relevant to machine learning, but still fit your backgrounds and knowledge. And you can start with this. And yeah, I think this is the advice that I can provide.
That is really insightful. Thank you so much. It's it does not always need to be in the most popular field. It's something that you're able to understand and interested in, and you'll be able to work in it. That's definitely true. So thank you so much, Jiayu. That was a really great session, and we had a lot to learn from it. Thank you so much.
Yeah, thanks.
Well, now at this point, we will have Manpreet taking us through the next round of panelist discussion. So Manpreet, carry on.
Hello everyone. Thank you for joining us today for the meetup, and I hope you're still enjoying and learning a lot with us. Moving ahead, we have a Women Shaping the Future of AI workshop, wherein I'll be moderating and talking to some of the women out there in the community who are doing such awesome stuff. So introducing from the left, we have Lee. She is an AI resident at Facebook and has been named in the list of top 10 young writers in China. Well, a fun fact, she's writing a sci-fi novel right now. Next, we have Samira. She is a machine learning engineer at Google and has been working on search ranking, representation learning, graph representation learning. She has numerous research publications in machine learning and deep learning in various scholarly journals. Next, we have Tejamode. She's a research intern at Vector Institute, wherein she is working in the areas of security and privacy for the machine learning. She is one of the founders of AI Saturday Logos from an artificial intelligence community in Lagos, Nigeria. Last but not the least, we have Mona. She is a research scientist at Facebook AI, where she contributes to developing systems with human level intelligence and also a full professor at the George Washington University School of Engineering and Applied Sciences. So I hope you have a great learning from them. And moving ahead, we have the first question for our speakers out there. I want them to discuss about what they think about the ethical challenges of AI, the future of potential of AI regulations, and the role of women in this whole process. Um, Anyone could go ahead, like Lee, if you could want to go ahead with this first.
Hello, everyone.
Okay.
Okay, so I think some of the ethical challenges of AI that I see include the fact that people don't understand AI very well, and they have an unrealistic expectation of what the scientific conclusions it reaches mean. So like, I think there are the people who think that we're going to like have all these killer robots like terrorizing the community. And then there are the people who think that if we have like a model that is that reaches a conclusion that like someone is a certain way, or like something a certain way, then that is like the absolute truth because it's science or because it's math. And I don't really understand like what like how to navigate like the black box, and like this leads to a lot of misconceptions and like very like bad when like it ends up in like predictive policing, and like you know, when people actually like take these models for granted because they don't understand how it works. So I think it's very important for people who are underrepresented in the community to raise awareness around this issue, so that this is not, you know, we don't just like charge ahead and like make an impact where like the issue is like very important.
Mona, what are your views on this, as you have been into this industry for a very long time? How the role of women in this whole process is challenging?
Yeah, well, first off, thanks a lot for inviting me. And it's really exciting to be part of this panel and this event, especially in Africa, which is dear and so dear to my heart. So yeah, with respect to the ethical aspects or ethical challenges, I think I agree with the Lee. But also, if we're thinking about ethical AI, it has a dimension of democratization, and that's very challenging. So how can you afford accessibility to information to everybody in their local language, given the disparities in income, therefore disparities in education? So how do you actually do this in an equitable way? Is one big problem. And that's also coupled with the transparency angle, and basically how can you make people not be afraid of our technologies? So that's one other angle. The other thing when it comes to you know, the role of regulation and so on, I'm a big proponent of having regulation, especially because our technologies could actually be misused or abused. So it's definitely a big problem. When it comes to regulation, it has to apply to everything from inception to data to the whole pipeline, basically. So this is one angle. Now, the role of women, we are half of the population of the world. So, you better use us. So, so in a way, it's like, what does it mean to design something without having the input from women, let alone diversity and inclusion? It's sheer brain power. We should be there at the table, helping out with all the phases, all the decisions, and coming up with all the solutions. So I'm just keeping it at that.
Well, thank you for such an insightful answer to this question. Moving ahead, I would like to ask Samira, what do you recommend for women who want to work in AI now?
Yes, can you hear me?
Yeah.
Yeah, thanks for this amazing event and inviting me to be in this panel. It's really great opportunity for me as well. And yeah, the question, first maybe for those who want to enter the AI field, the one thing that maybe I can recommend that build up and strengthen their technical skills, and with maybe start, if they are very new, they can start with just taking online courses. There are many, the AI is very open field, and there are many already open resources that everybody in every part of the world can just do self-learning. And then there are a few steps that, okay, you build your foundation. Maybe if you want to maybe learn more about just the mathematical aspect, learn more linear algebra or a statistic, and then start pick some a problem that you are really excited and interested about that topic, and read a few main papers in that topic, and try to get familiar with for example, the code base, and play with that, and even reproduce the result. And also the one more important thing is that try to find some a mentor. It's really, I think, for every maybe junior researcher or even later in the career, it's good to have some a mentor to guide you and keep you motivated. And also try to be in some a team that they are supportive, your colleagues or maybe supervisor or anybody that you are working with. It's very important to be in a supportive and environment that is not toxic to not very encouraging for you, and that is very important in building your career as well. So I can specify the two factors that a mentorship and also being a very supportive environment. And I think all of this is positive. I mean, nowadays, as I said, it's an open field, and many people in every part of the world, they are basically there to mentor new people that they enter the fields. They can, for example, the programs that Women in AI, Black in AI. So junior people, they can attend these events or meetups and try to network with other researchers in the field, and try to basically find someone that can along the way guide them to find their interests and work on some a research problem from start to the end, because maybe the path is sometimes difficult. Maybe you don't get the result or any outcome in the short term. So it's good to have a support and guidance of some other person. Yeah, I mean, these are the things that it comes into mind.
What are your thoughts, Tejamonde? Because you are an intern still and you are a student. So what do you think around this thing?
Hi, everyone. Thank you so much for having me. Really, Samira has said a lot of what I wanted to discuss here, but yeah, just to kind of touch more on what you said, it's just I think it's important that, you need to if you're trying to master a skills, you have to take your technicalities seriously, and maybe one of the things that technicals are very it takes time from experience. It's just most people start, and then they kind of get excited about machine learning, and then you try to let them that, like, you know, this is just like the cherry, like you need to like make sure you hone your background and what's not. So I think it's important to start like exposing people to sort of like all of this important concept they need to also understand, you know, not just like make it field was open enough for people to be interested in it. Now we need to like make sure that we the skills are solid, and then we are able to, you know, improve on our stuff if you're looking to like have quality you know, people addressing very important problems. And just also to touch on some of Samira's point is that in my experience, I think it's very important to have a research interest. It's sort of like just give you this calmness, like it directs your focus. So you can still learn, and you should definitely still like learn other stuff, but once you have a research direction, something you're thinking about, you're able to like go down into that and then try to understand what's happening in that area without feeling begin from like there's just too many things going on a research interest. Then you can look for mentors, like for people in that specific domain. And just like Samira said, there are a lot of people out there available, willing to share their experience with you, willing to teach you, but you just like gotta be interested in what they're interested in, because they have specific skills they want to render. And yes, she already mentioned the importance of like working in the supportive environment. One of the things that I have found very like I have, you know, intern at a research lab where I have like I have a supportive environment with my supervisor and all my other researchers. And you know, as a student, it's kind of like just help you like you see other students, what they're going through. It inspires you in some way. And so that's sort of that supportive. So I think just to add to it, really, she said it all. And yes, thank you for asking me to chip in.
Well, thank you so much for such an insightful and creative insights to this answer. Well, we all learn and grow from each other every time. Moving ahead, how to overcome the challenges faced by women while pursuing AI as a career, surviving graduate school. So, I guess I would like Mona to go first with this question.
Can you hear me? Yes.
Yeah.
Okay. So graduate school is typically tough. And I think one thing to recognize is that people who make it, they're really perseverant. So really, I think it's about perseverance and having grit, meaning that you just stick with it. You don't take, you know, failures as a sign of anything beyond a learning experience. So basically adopt a growth mentality as opposed to a victim mentality. That's extremely important. And recognize that graduate school or a PhD is really about teaching you about the skills of how to follow the scientific method. It's not really about the subject matter per se of what you're pursuing. It's about the process and sticking with it, knowing how to go through the scientific method methodically, systematically, and learning that and being able to apply it to things that, and of course, if you have the passion to top that off, that would be fantastic. So I think that's extremely important to maintain a growth mentality, learn from your failures, and have resilience in the sense of, you know what, I'm going to stick with it, and recognize and, you know, celebrate your accomplishments, because, you know, only 30% of the people who go through a PhD actually make it out. So, and it's not because they're stupid, it's because it's, you know, they just give up. So it's about perseverance and sticking with it and resilience.
Well, thank you so much for highlighting such a wonderful point of learning and keep learning from everything and have that learning attitude. What is your view, Lee, to this thing?
So I haven't been to graduate school, so I can talk a little bit about AI as a career. I think it's very helpful to find, I mean, like, it's like our software / computer science, like it's very like male dominated. So I think AI is not an exception to that, and it's very helpful to like find like a community like this one that we're in right now, or like Grace Hopper I like a lot because just like the sheer size of it, like you get to meet like all these like people, whereas like in usually it's like I went to this other conference at some point, and there was like a line for the bathroom, and I was like, oh no, there's a line in the bathroom, but then I walked up to it and I realized it's a line at the male bathroom, and I've never seen a line in the male bathroom before. So it's like, it can be kind of like isolating, I think, like when you're like dealing with this every day, because there's not a lot of people who look like you. But it's nice to like seek out the community like intentionally, and like to just like be like, oh, there's like a ton of people here who have like a similar experience. So I think that's like one thing that I find really helpful in a career.
Well, thank you for that. Moving ahead, I have a question for you. The gender imbalance in the AI space. Do you think we need more female AI researchers, practitioners to secure an unbiased futures? How a woman's thinking can make an impact to this? What are your views, Samira, to this?
Yeah, so I think as Mona mentioned at some point, like women are like half of the population, so it's not rational to just like push out some like a person like this half of the population not to be in the field. And I think okay, I mean based on the statistic, I mean so far maybe it has been a bit more unbalanced, the population of people or researcher and like engineers working in this AI field. It's been towards maybe a specific gender and a specific like demographic. So that also makes the basically these engineers and researchers to work on some like maybe a specific problem that maybe it's more towards the goals or like problems that they are known to that specific population that they are currently actively working on this field. I mean, there are, for example, problems that maybe women are the kind of problems that women think maybe none of the maybe men don't think about that, or like it's not important for them. So I think to have a diverse set of problems in AI to be worked on in the future, and also the solutions for those, like in terms of like maybe addressing the bias, for example, the different languages. There is like, for example, if you are work on NLP, there are like different languages. It's not just English. So maybe those who are just native languages English, they will work on some, for example, in terms of, for example, language models, it's good just for like English speakers. And there are many languages in the world. If there is not like a researcher that actually has been like a native from that language to work on this field, then it might be the case that these are like a biased or like a imperfect in terms of like some statistical some like groups of people in the world. But still we are targeting, for example, the users of that product, or like a project that get launched is like millions and billions of people over the world that they are coming from the different background. So not just the women, I can say that all the like demographic groups, all the like different from different races, different countries, they should be really considering to if they are really interested to not be scared to get like start working in this field. And maybe it's also the others people that they are already maybe well established in the field to support others from other groups to make it easier for them to enter and be have a supportive environment for them. Yeah.
Yeah, well, there's a very famous quote that if a man is educated, he educates his children. But if a woman is educated, she educates her whole family and take care of her family. So maybe what a woman might think can never be taken by the other people in the community. The way she thinks about things could make a really good impact in our AI community coming ahead. Moving ahead to our next question, we have discussed some strategies for designing and developing exclusive AI products. What are your thoughts to this, Teja Monday to it? Yeah. Anyone else could take up this question? I guess there was some net connectivity issue.
Yeah, I can maybe also mention some few things about this. So I think the first main thing is that make a like, for example, for different products, companies work on different products to build a diverse team that like there are engineers and researchers that working
Yeah,
and are
so
active. Oh, okay. Yeah, just maybe I just finish quickly that work on that project is I think the first step is to have like people's working and involved in that project to being like from maybe a diverse background or expertise, and or even like again like a group, so like a race or like a gender.
I can jump in if
yeah.
everybody else, yeah. I completely agree with Samira, and I want to say something about collaboration. And I think this sort of crosses over into the previous question. Women tend to be very collaborative, so that's something that is a boon for having women on a team. But also the notion of empathy is something that I think could be thought about from the get-go when we're building AI products. So how can we build more empathetic systems in our processes?
Yeah. Anything, Lee, you want to share on this?
I think something that I kind of just want to throw out there. I think like we already made really good points. Definitely agree with all of that. I think something that is important is like the ethics of like where our data is from, and like so we know that like if our data is bad, then like garbage in, garbage out. So I think it's very important to also like look at like the ethics of like how that data is collected. And I think that's kind of like a very hard question that we're kind of just coming to looking at right now. Like because like a lot of times like the companies or the governments or the institutions that have like the power of like collecting this data like are often like have like too much power. So and or like they're like collected through like unethical means. Or like they are collected in a way that is like inherently like not inclusive. But on the other hand, like if you're a scientist, like you might not have like data is very expensive, and like you might not have the means to collect this data yourself, and like you would really love to work on it. Right? We would all love to work on like a project with really great data. So I think this is like I think it's important to open up the conversation if we want to build inclusive AI products, to open a conversation on like how do we like it's not just a personal ethics thing. Like you can't just be like, I'm not going to work on it because other people will, right? And I think it's important to like make this a priority where like we build a process for like making the collection process more equitable.
Thank you so much for that. As you said that who would love to work on data, because everyone wants good and clean data to work on their perspective problems, and it plays a very important role. Teja Monday, do you want to share any views on this topic?
Yeah. Sorry, I thought you mentioned me before, so I cut in. So I just just wanted to share that, like, really, if you're trying to build, you have to take more seriously building a diverse team. Like, companies to take their DEI a lot more seriously, because if you have diverse team, then you have diverse perspective. People have different things that affect, they're not even thinking of. Your teammates might be thinking of it. So where you're falling short, then other people might be like, oh, no, why are we doing X? Why don't we do Y? And then, so that's sort of like helps you build, like, in my opinion, helps you come up with products that does not just work for some part of the region and not a field, in terms of like for all. It works for a field. The researchers here intended, but we gotta like make sure that it's not about intent, and that we need to like continue to improve and continue to do whatever it takes to make sure that we are representing all of the come here to service with a product, especially if you're building a global product. I think it's not an excuse to kind of like marginalize out some. I can think of it's just like you have to like look internally, make sure that you have a well-represented group of people, like brilliant researchers, and then come up like this, like people are here to like solve problems, right? Like let's come up with strategies that doesn't just like work for some group of people, but like is able to like work for all, trying to serve. Yeah, thanks for asking.
Well, thank you so much. Now moving ahead to see what audience has to ask you, and we'll be soon asking to see what audience has some questions stored up for you.
Yes, thank you so much, Manpreet, and thank you so much, Mona, Samira, Lee, and Tajumat for that amazing, highly engaging and lively discussion. We have a couple of questions we would like to ask on behalf of our attendees. I think we can ask this one first. So what have been some key... Yeah, sure, you can go ahead.
Well, I would like you all to answer this, that what are some key takeaways from your journey so far which can help every aspiring woman or anybody who is coming into the field of AI. And I would like to go, if it would be like dictionary wise, you can go ahead and everyone could speak on this. Like firstly, you can go on this.
I think a key takeaway would be how important it is to believe in yourself and like believe in like your perspective, like as a woman and like just as a person, like as a specific woman that you are. How important like that is to helping shape the conversation and like helping like build like the different projects that wouldn't have been there. I think it's very common for women to kind of sell themselves short and like to have self-doubt, and I think it's important to really like believe in like what you're doing so that you can continue to work on like things that that matter, because they do matter. And this is kind of what we've been discussing. So I think it's important to keep telling yourself that and to surround yourself with people who can lift you up.
What are your thoughts, Mona, to this? What are some takeaways from your journey that our audience could take away?
I think Lee said it really well. It's really believing in yourself, believing in your vision, and stick to your passions, be authentic, and don't let things derail you, and essentially recognize your contribution, recognize your perspective. So I totally resonate with what Lee had said before, but also, again, grit and perseverance and resilience all over. And try to avoid the victim mentality. Even if you think of yourself as a minority in the field, you have a unique perspective that should be valued. And if they don't value it, then they're not worth it. Move on. So.
What are your thoughts, Samira, to this?
Yeah, I think others mentioned very great points, and I also believe in believe in yourself and self promotion. Maybe I can just add a few things that maybe don't compare yourself to others much along the way, because people are with different paces. For example, in publishing papers or getting a jobs. I mean, take it just a step by step according to your your condition. So I mean, all the people are not the same, so they have different basically professional path and career, and it's just every person has some unique way. Or even entering, for example, in AI, people are coming from different backgrounds, coming from the math, physics, or even philosophy or so. And I think the AI field is very collaborative and also diverse, and many fields are interdisciplinary and many problems. So even if you are not so far you haven't been working related machine learning problem, but you are really interested, passionate about some problem or topic, I think you can still enter the field and work on something that maybe your basically add your expertise to the field. So you can work on machine learning in some application in the domain that you are already expert. So yeah, I mean, just just to summarize how it's a self-confidence, be patient, and find good mentors and surround yourself with supportive and non-toxic people along the way.
What about you, Tejamonde, to this?
Yeah, sorry. I've been going on and off, so I didn't catch everything. So I definitely agree with Samira's point, the ones I caught, which is self-confidence and being patient with oneself. For me, I like to see most of what I do as experiments, and just experimenting, some fail, some succeed, and it's okay. So once you kind of you have an interest and you have it, sometimes you commit to something, and then it requires a lot of grit, just Mona said earlier, and perseverance. And so once you commit to something that feels like it's higher than yourself, you kind of just continue to work towards being the best version. And you have to be, in my opinion, it's just just be okay with whatever it is you call failure. It's just about learning. So it's not really about failing or whatnot. Don't be afraid to try new things because you don't want to feel at it or whatnot. You laugh at yourself once in a while when things does not work out the way you think it's gonna be, and then you can have 1 or 2 days of not feeling good, and then you pick up the race and you continue, because that's what life is. It's just gotta continue to show up. You show up for yourself. It's very important, not just for others, just make sure you show up for yourself. Because so, and the key takeaways from my journey, really, it's just about having strategy. Usually when I think back to how I got here, it's thinking long-term and short-term. There's some things I know I can achieve in short-term, but there's some goals I'm looking at for long-term. So even though I know that they're long-term, they're in my rear view, I can think about them. I'm okay with things changing, in the process. It's not very rigid, but I have an idea of where I want to get to. You get what I'm trying to say? So, and it's not about trying to please this person or this person. Like I said, it's always about you showing up for yourself and also committing to goals that like feels bigger than yourself. I like serving the community. I care about a lot of other things, and then those kind of things like pushes me and want me makes me want to be better, do better. Yeah, so I'm gonna stop here because I know we're out of time.
Well, thank you so much, Tejamonde, Mona, Lee, Samira, for joining us today and sharing such insightful and, that could help our community so much now, and especially inspire so many moving out there to come and take the charges and do so well. And thank you so much for being here, and all the viewers continue, and now I'll be handing it over to Raman to take the session forward to it. Thank you so much, everyone.
Thank you so much.
Thank you.
Thank you so
and
much.
Nice to meet you all.
Thank you so much.
So moving on from here, thank you for the amazing moderating the session, Manpreet. I will now I would now like to invite our next speaker on board, Junzi Zhang, who is currently a PhD candidate at Stanford University. He is a final year PhD candidate at Stanford ICME. Junzi is passionate about data science communities and was a mentor in the new machine learning forum at NeurIPS 2019 and 2020. He has published multiple papers in peer-reviewed journals and conferences, including SIAM Journal on Optimization, SIAM Journal on Scientific Computing, NeurIPS, and ECML. And his research has also led the improvement and creation of some open source optimization solvers. He has served as a deep learning researcher at CloudBrain AI and a quantitative researcher at Citadel. He's a math enthusiast and a big fan of music, singing, and playing accordion, trombone, and the kuaiban, which is a traditional Chinese percussion instrument that has always been his best relaxation method. Today, he'll be talking about new discoveries of old wisdoms for faster optimization. So welcome, Junzi, and now I'm going to let you share your screen. Thank you so much.
Thank you so much. Thank you so much for the introduction. Let me try to share my screen. Can you see the slides?
It's visible. Yes.
Okay, thank you. Hi, everyone. So my name is Junzi Zhang, and it's great to join the NeurIPS Nairobi Meetup today. And in today's talk, I want to share some new discoveries of some old wisdoms for accelerated or faster optimization. And I created this fancy name, but basically what I want to do is just I want to share some classical tricks that actually turn out to be working super well, and they are revived, improved, or rediscovered recently for accelerated optimization. And so this talk is partly based on joint works with my advisor, Professor Boyd, and also some of my collaborators from Stanford, Berkeley, DeepMind, and also Oxford. Yeah. So in today's talk, I will talk about mainly two types of old wisdoms. The first one is problem reformulation, and the second one is fixed point extrapolation. And this can also be seen as a kind of algorithm reformulation. And so let's first take a look at the first type of wisdom, which is problem reformulation. And in this type of like philosophical tricks, the first most common one is to convert from a non-convex problem to a convex problem. Many problems, as they are formulated directly, they are non-convex. Actually, with some small tricks like change variables, typically, you can just make it a convex problem. And let's take a look at a like warm-up example, which is taken from a standard textbook. Let's say we are like estimating a Gaussian random variable. We're doing covariance estimation of a Gaussian random variable. And then the negative log likelihood function to be minimized look like this. And it turns out to be non-convex in the variable sigma, which is the covariance matrix. But a standard trick is just to use the inverse covariance matrix as the variable instead, or the precision matrix. and then the problem turns out to be convex. Let's take a look at a more interesting problem, matrix equilibration. And in matrix equilibration, we're actually wanting to find two invertible diagonal matrices D and E, and make D and E to have the same LP norms for the rows and the same LP norms for the columns as well. And of course, like the column norms and row norms, they can be different between from each other. But for different rows, different columns, we have the same norms. And you can just write out the problem by definition as a feasibility problem like here. And it turns out that this is also a non-convex feasibility problem, because in general, like you're only allowed to have affine constraints for economic constraints if you want to formulate a convex problem. And so can we also make this problem a convex problem? And the answer is yes. And the way we do that is to find a convex opposition problem where these feasibility conditions like here, these two constraints, become a KKT condition of the reformulated convex problem. And it turns out that if we do a change of variable, exponential change of variable, then we can formulate this convex problem in variables u and v jointly. And if you take the KKT conditions out, write down the KKT conditions, you find out it's actually exactly the conditions we write out here. So it's actually now a convex problem where solving it is equivalent to solving the original non-convex feasibility problem. Another example is if we consider joint covariance estimation and linear regression. And so this is a little bit different, like the extension of the previous, the first example, where we only estimate the covariance matrix. And it turns out that the negative log function is also non-convex jointly in the C matrix, which is the coefficient or regression matrix, and the covariance matrix sigma, which is natural because even if you fix C, like let's C to be known, it's non-convex in sigma as we have seen. And with a similar trick, we can make change variable of sigma into S. Like we take the inverse of the covariance matrix as a variable. In addition, we can define a matrix B to be the multiplication of C and S. And it turns out this problem is convex. And this trick is pretty powerful because actually, like not until this year's NeurIPS, this new paper, this result was unknown. So people have been using non-convex approaches to estimate jointly the covariance matrix and the regression matrix. Yeah. So these three examples give us some idea of how we can transform from a non-convex problem to a convex problem. For many like modeling like researchers, this might be the end of the story. So we're done because convex problems are polynomially tractable in general. But if you're a practitioner, if you're already solving the problem using software, using code, then this is not the end of the story. And you will want to think about how you can solve a specific form of a convex problem as well. And this leads to the so-called standard form for solver design and selection. So the important fact here is that although it's true that in theory, all convex problems are tractable from a theoretical viewpoint, but some of them are more tractable. And also, in general, if you really want to solve a problem, you have to reduce it to some standard forms. Otherwise, in general, you cannot really solve the problem by its original form. Despite that, in theory, you can do that, but you have to resort to some software, you resort to some existing algorithm usually to solve it. In that case, you have to find some standard forms as an interface between your problem and the actual code. And some common examples of standard forms including linear programming, quadratic programming, SOCP, SDP, or there are also some solvers or like standard forms of generic cognitive programs, including all these different cones and also like power cones and exponential cones as well. And also there are some more application-specific standard forms like portfolio optimization, commodity flow, LeSU or ARMA, and so on. The general principles of choosing or specifying standard forms in the solver design, if you're someone who writes solvers, or solver selection or choice, if you're someone who are using solvers, I think that there are two principles. The first one is that you should always choose the more specialized form. So for example, if you're solving a quadratic program, then it's almost always better to use something like OSQP, which is tailored for a quadratic program only, instead of SCS, which is tailored for very generic cone programs, including QP, but also like exponential cones and so on. The second principle is to choose a more compact form. And this is something I want to explain in the next few pages. To illustrate this idea, I will want to introduce a recently revived standard form called proxifying form. And this form is less commonly used in existing solvers, but they're actually much more efficient in many cases. So a so-called proxifying form is a form that is used in some solvers like Epsilon and also A2DR, which is a solver we produced last year. So a proxifying form is basically just a problem where optimization problem where the objective is represented as a summation of block-wise separable objectives, and the constraint is just a linear constraint. And of course, as you can see from here, it may look like it's a linear constraint optimization problem. So some problems cannot be represented. For example, if you have a cone constraint, but actually we only assume that FIs, each of the FI are closed convex proper, so they can be non-smooth in general. And so if you have a cone, you can just make it indicator function and put it there. And also we assume that each FI can only be accessed through their proximal operators, which is basically minimizing FIXI plus a quadratic term. And in fact, it turns out, if not all, at least like 99% of the convex optimization problems can be represented in this way, and without much loss of efficiency. And also, you don't really need to do a lot of complicated things. So before we move to that, to explain about how we transform problems into this form and how it compares to some other existing standard forms like conic forms, let me first make two quick remarks on the proximal operator, because it may look a bit weird, like here you are doing almost a minimization of each FI, but just plus a quadratic term. But actually it turns out that this can be seen as a generalization projection. So if you have an indicator function, like an indicator of a cone, for example, you're projecting onto this cone. And also for many, the proximal operator have a closed form, or they can decompose into a single dimensional, one-dimensional equation solving. So they're generally like a closed form. And so actually adding this quadratic term usually save you a lot of difficulty, and you can actually just compute the proximal operator in linear time in many cases as well. All right, so why we consider this proximifying form is basically can be attributed to three reasons. The first one is separability. So as you can see, in this form, the objective is block separable, and so you can utilize, you can just perform proximal operator of each block at the same time, which is suitable for parallel and distributed implementation. The second reason is black box, because we only assume that access to proximal operator. So you can easily allow peer-to-peer optimization with some privacy requirements. For example, you can just use some sort of private protocol to encode your proximal operator, and you don't need to share your data or let people to calculate the gradient or something so that they might be able to review the data. And the last one, which is actually the central one that we want to talk about here in the next page, is because they lead to much more compact representation in general than the alternative conic standard form, which is very widely used in existing solvers. Like almost all the solvers called by CVXPy or YAMIP fall into a conic standard form, which we'll talk about in the next page. And cone programs, conic programs, these standard forms can be represented as in proxifying form by just consensus variable sharing without any complication in general. Because actually in these conic solvers, they almost all did automatic consensus sharing. But the other way is not correct. So basically, if you have a proxifying form and you want to, or you have a general problem, you want to transform it into a, or reform it into a cone program, you will probably get into a very complicated formulation, which we'll see in the next page. This is especially the case if you have logarithm, exponential, and determinant involved. And in these cases, the proxifying form will be much more compact. So, so before we take a look at an example showing this like difference in compactness, let's first take a look at how we can represent a conic form as a proxifying form. So a so-called conic form is basically just a quadratic objective subject to a linear constraint plus a cone constraint. And in many cases, the Q is just 0, like in many other conic solvers like SCS and echoes and so on. And this form, as I mentioned, is using most of the solvers, and also they are targeted standard forms of most of the modern languages like CVX, YAML, and so on. They will just help you transform more higher level description of the problems into the standard form. So you don't need to do that. But in next page, we'll see that although they help you get rid of this trouble, you may end up into some additional trouble because the problem could be very complicated and the number of variables will be much larger, much more than if you transform it into something like a proxifying form. And it's easy to write the conic form into a proxifying form. And this is done by just creating a consensus variable sharing. Basically, we just put the cone constraint into the objective as an indicator function. Then we create a copy of the variable x1, x2, and make them separated so that we can evaluate the cone constraint as a proximal operator as a projection onto the cone. And this part is just a linear system solving. And the other way, then let's take a look at the example showing that the difference between the compactness of these two forms. So the example we look at here, the first example is a portfolio optimization with transaction costs and risk constraints. So here, this absolute value term and this 3/2 term, they are the transaction costs. And this is R transpose X is the mean return. And this constraint is, first constraint is the risk constraint. And second constraint is just saying that it's a portfolio always sum up to 0. Sum to 0, including like some short selling opportunities. So if you want to represent into a standard conic form, which is accepted by Mosaic, Groby, and many other solvers, then will result into this very complicated solver, and a very complicated problem formulation. And you can see that the original problem, if it has an n dimension, like here, x1 to xn, then now you will have 9n plus 1 variables. And also, if you really want to solve it, you have to create additional consensus. And this will lead to much larger dimension than 9 plus 1. For proxifying form, the rewriting is much more straightforward. You just need to create 5 different variables, and you're done. And you don't need to create any additional consensus variable copies. You can just invoke epsilon or A2DR and other similar solvers to solve it. And the second example is an example that we want to show about the actual running of runtime, or like basically the numerical performance of solving a problem with proxifying formulation or versus a conic formulation. And here we compare A2DR and SCS version 2. Both solvers are produced by me and my collaborators. I mean, in terms of, especially for version 2 of SCS. So, and they both include energy saturation component. So the major difference here is SCS is a conic form solver, and A2DR is a proxifying form solver. And here we solve this covariance estimation example, but plus L1 norm constraint. So it's a sparse, so-called sparse inverse covariance estimation problem. And for this problem, we tested two problem sizes. One is with n equal to 1,200, and another one is n equal to 2,000. And we can see that in this case, A2DR took 1 hour to converge to a tolerance of 10 to the minus 3. And in contrast, SCS with the conic form took 11 hours to just achieve a tolerance of 10 to the minus 1 and yielded much worse objective value. For the second case, which is a little bit larger, A2DR converged in 2.6 hours, while SCS immediately failed due to out-of-memory error, which is caused by the consensus sharing and so on. Yeah. So this illustrates that actually, even if you are already solving a complex problem and you have existing solvers, you might be more careful in selecting appropriate solvers for a purpose. So for example, if a problem involves a lot of logarithms, determinant, exponential, and so on, then probably you will be careful about using conic solvers like SCS, Mosaic, and so on, especially if the problem is large. So these are the solvers I mentioned, like Epsilon, A2DR, and also there's another solver which transformed into a similar form, which is not process form, but it's closely related. It's called graph form. And so if you're interested, you can also take a look at this solver. All right. So this is so far, like if you are someone who are not really an optimization expert or someone who do optimization research, this is probably the end of the story. But if you are really someone who wanted to do some research in optimization, then the next wisdom I want to share is something that you may be interested in. So as we have seen, like for a non-complex problem, you can transform into a complex problem. And for a complex problem, you may have some idea of how to select a standard form to solve it. But even with the standard form, you have to design some algorithm to solve it, like gradient descent, like ADMM, and so on. And the following part, I will talk about a way to accelerate solving, accelerate many existing algorithms or solvers with very simple tricks. The tricks I will talk about are basically two. One is a fixed point reformulation or perspective of the algorithm iteration. And the second one is using extrapolation to accelerate performance, both stably and fastly. All right. So the first one is, as I mentioned, is a way to view algorithm iteration as a fixed point mapping. And this week actually make it possible to like design or apply like extrapolation methodologies or acceleration techniques on top of existing algorithm solvers without breaking down or looking at the inside of the solver. So you can actually pull out a code, and you only need to know what's the per iteration update. So for example, given the xk, how you get what's xk plus 1, and then you can just apply the acceleration on top of it, which is very easy and in a black box and easy to use. All right, so many algorithms in optimization and also control can actually be reformulated as a fixed point iteration, where f equal to fv if and only if the optimality condition holds. And here the v is just the algorithm state, like iteration, and f is algorithm iteration mapping. And there are so many tons of examples for this, like projected gradient descent, variation, dark square splitting, ADM, and so on. But I'll just mention two of them here as an example. The first one is projected gradient descent. So let's say we're minimizing fx subject to x belong to some complex set C. Then a projected gradient descent is basically taking gradient step and doing a projection. And the optimality condition, you can actually write it as x equal to fx, where f is just the projected gradient update with k removed, the index removed. And you can show that actually x equal to fx if and only if x is the optimal solution for this constraint problem. And also, this fixed point mapping have very good properties, like they are non-expansive. Basically, they have a Lipschitz constant of 1, and also they are actually indeed they're averaged. So by average, I mean it's a mixing of x plus some non-expansive operator, but it's not really relevant to the subsequent discussion, so we can just feel free to skip it. And the second example is is validation for solving MDPs. And variation, as probably many of you already know, is just doing a fixed point iteration using the Bellman operator. So naturally, the optimal condition or reformulation of the variation at the fixed point is pretty straightforward. It's basically just a Bellman equation. It's V equal to FV, where FV is one-step improvement of the value function. And again, you can show that this F has good properties. And here is gamma contractive in L infinity norm. Basically, it's gamma Lipschitz in the L infinity norm. All right. So having seen that, how we can transform an algorithm iteration into a fixed point mapping. Now, the question is, in general, like solving or running fixed point iterations will not be very efficient. It could be pretty slow. And secondly, like up to now we haven't done anything but just providing a viewpoint of seeing an algorithm from a different way. So that doesn't help at all in general. So the next part I will talk about recently revived approach called Anderson acceleration. And this approach allows us to accelerate very, very general fixed point iterations or fixed point mappings without really knowing details of what's inside the fixed point iteration. So we can accelerate algorithms in a black box way. All right, so acceleration is actually, before we move on, just one quick comment is this type of acceleration techniques actually dates back to 1960s. And recently it was seen as rediscovered for optimization and machine learning. But before that, it has been already widely used in computational chemistry and physics, material sciences, and so on. Yeah, but it's not until very recently that this approach has been seen as a very good fit for optimization and machine learning. All right, so by acceleration, like acceleration, for example, which is an example, what we mean is actually just taking some previous MK iterates and also their next iterates, like fixed point mapping of these iterates, and do some mixing of them to produce the next iterate. And this phi k can be linear or nonlinear. And there are many examples of these. The first one is just the KM iteration or average iteration. Basically, you just mix the fixed point iteration with something with the current iterate. And beta is basically generate something between 0 and 1. And for gradient descent case, if f is gradient descent, then the KM iteration itself is still a gradient descent algorithm, but just with a different step size. The second example is momentum method, like heavy ball approach or Poyak's heavy ball approach. And here, the memory is 1, and we basically just take the fixed point mapping plus momentum term. And the third example is inertia method, and we basically just take a mixing of the fixed point mapping of two successive, most recent iterates. And this actually leads to natural acceleration if you are considering f as a gradient descent mapping. The Anderson acceleration is basically another way of mixing these previous iterates. It's basically taking a combination of previous MK iterates, where MK is general, and we select the coefficients alpha jk here by solving a least squares problem. And this will lead to the so-called Anderson acceleration or type 2 Anderson acceleration, which basically just mixing the previous iterates using coefficients solved from least squares problem, as I just mentioned in the previous page. There's also type 1 acceleration, which essentially also mix the previous iterates with the coefficient alpha jk, but just alpha jk are chosen in a different way here. This type 1 acceleration is discovered only in 2009, I think. Yeah, and it's less stable, but it actually works pretty well when it converges. All right, so So in terms of the performance of these acceleration techniques, so we can see that actually both type 1 and type 2 acceleration, they perform pretty well. And they actually accelerate, for example, here is a variation for MDP. We can see that they accelerate the vanilla variation by significant margin for all the memories almost. And actually for memories 5 to 10, it suffices. And this is in sharp contrast to like coordinate method where you usually need a memory of hundreds. So this is pretty efficient. But also they suffer from instability issues. So they can fail both for type 1 and type 2. And so to resolve this issue, several stabilization approaches have been proposed. And we can basically group these kind of stabilization tricks into 3 categories. The first one is regularization. Second one is adaptive restart. And third one is a safeguarding strategy. And they are adopted in the version of SCS, A2DR, and there is a non-convex solver called AAIPALM. And also the regularization idea actually dates back to 2016 by a different group of researchers who proposed RNA, which is regularized nonlinear acceleration, where they propose a constant quantum regularization and show that they lead to local convergence improvement in theory and practice. However, we have found that it's insufficient for global convergence in theory and practice. So we introduced some additional tricks. And finally, let me quickly go through some plots to showcase how these kind of stabilization tricks works, and also how they compare with the unaccelerated ones. The first one group of results are for type 2 acceleration. And here we can see that just the constant regularization in the RNA algorithm already improves quite a bit. And if we introduce additionally the adaptive regularization and safeguard, the performance is further improved, as we can see from the green curve versus the other 2 colors. For type 1 acceleration, adding these stabilization tricks can actually stabilizing the performance from divergence, as we see from the previous page, to convergence and acceleration. And also for many other cases, you can also see like a stable improvement over the non-stabilized ones, and both stabilized and non-stabilized ones generally outperform the vanilla ones quite a lot. And here we have seen many different algorithms, like here is gradient descent, here's ESTA for elastic regression, here's MDP solving. And also for SCS, as I mentioned, what we implement in the version of SCS, you can also see a very dramatic improvement over the unstabilized version and also the vanilla version, where the stabilized one is in orange. And finally, the last thing is about the non-convex cases. And here, one of the things I want to show is that in contrast to the previous ones, here one of the major role that plays a significant role is major thing that trick that plays a significant role is the safeguard. And here, if we just ignore the safeguard, then everything breaks down. And if we include the safeguard, then everything works both in synthetic and in real-world data set. All right, so that's all. And let me just quickly summarize some takeaway information. First one is that don't just go away with non-convex formulation. In many cases, you can actually reformulate it as a convex problems using just simple tricks like changing variables. The second one is when you choose solvers or when you design solvers, be sure to typically choose more specialized and more compact ones. And the last one is that there is a fixed point perspective and there is a so-called Anderson acceleration technique, and they are a generic workhorse for black box line search free and memory efficient acceleration. And they can be incorporated into many existing solvers to improve them very efficiently. Like SCS is one example. All right, thank you so much. And that's all my talk. Thank you so much.
Thank you so much, Junzi. That was a highly informative and rigorous presentation. We learned a lot from it. Thank you so much. If you can stop your screen share, sure. I will briefly ask you one question over our platform.
Thank you.
Yes, so let me ask this one. So in simple terms, what are some challenges in ML optimizers in highly distributed or like a parallel training settings? What would you say?
Got it. Yeah. Thanks for this question. I think this is a great question. So for distributed or parallel training settings, I would say one of the major bottleneck is communication cost. So although there have been many research papers discussing how to improve the communication protocols, like using local communication or asynchronous updates. But currently, I think this is still one of the biggest obstacles, both in theory and practice. And another challenge is actually the lack of available solvers. So although there are thousands or even tens of thousands of papers each year in distributed optimization, but almost none of them or very few of them actually can be used off the shelf. Even some very popular ones like Cocoa or Cocoa Plus, they are working pretty well. But they generally, if you want to write solve a problem of yourself using the framework, you have to rewrite many things from scratch, like even some algorithm details, because they just provide some example implementation with these specific problems. So I think these are the two major challenges I would see from in this distributed and parallel optimization field.
Thank you so much for answering that question. I would also like to, at this point, remind our attendees to keep using the Slido link to ask further questions in the next two sessions. So at this point, I would like to invite our next moderator, Samira, to start the next session. Samira.
Hello, Ramanj. Thank you so much. Am I audible?
Yes.
Okay, let me quickly share my screen. Is it visible now?
Yes, it is.
All right. Hi, everyone. I hope you're all having a good time today. I'm really excited now to invite Rishabh Mehrotra as our next speaker. Rishabh is currently working as a senior research scientist at Spotify Research in London. His main research interests lie around developing scalable learning systems which power multi-stakeholder market platforms. Rishabh has a Ph.D. in machine learning from University of London, where his focus was to develop efficient Bayesian and deep models for user understanding, knowledge discovery, and decision optimization. During his PhD, he was also a research intern and visiting scholar at Microsoft Research, where he worked on fairness in searching and learning algorithms. He has many peer-reviewed publications in scholarly journals and on machine learning and deep learning research to his name. He also co-founded usercontext.ai, which provides deep learning solutions around understanding user tasks based on cutting-edge machine learning methods. These help businesses in providing their users with personalized and proactive task assistance. Not just this, Rishabh is also an astronomy enthusiast, and he has recently got himself a telescope to observe an upcoming conjunction between Saturn and Jupiter later this month. On behalf of the whole team, I extend Rishabh a hearty welcome. I'm sure all of us are enthusiastic to hear what he's got for us today. Over to you, Rishabh. I'm just stopping my screen share so that you can do it.
Thanks, and I'll try to screen share. Okay, I hope it works.
It is visible, yes.
Just a moment. Perfect. Thanks so much for the kind introduction. So my name is Rishabh. I'm joining from London today, and thank you for joining us in this NeurIPS Meetup. So here today we're going to talk about how do we optimize multiple objectives for recommendations in marketplaces. So essentially, what we're going to do in this talk is I'm going to briefly talk about the recommendation problems we face at Spotify, and then directly jump on to talking about recommendations in general, like the typical recommendation scenario, which is user-centric, and how can we evolve that to multi-stakeholder problems. Then I'm going to briefly touch upon work we did on bandit models, so contextual bandit models for the homepage recommendations on Spotify, and then I'm going to mature our discussion towards more multi-stakeholder problems. So in general, I did my PhD from UCL. In general, my PhD interests were on search task understanding, but more recently I've been looking at machine learning for marketplace. So if any of these topics are of interest to you, I'll be happy to hear from you. So in general, if you look at Spotify, then my team's mission is to connect listeners and creators in unique and enriching way. So right here, you see that we care about not only the users who are consumers of music, but also the artists and creators on the platform. So essentially, to do that, we have to look at recommendation problems at scale. And in general, if you look at the number of tracks, then this is like 60 million plus tracks. So that means the recommendation problem is of prime importance here. because there's no way we can expect users to hunt through these millions of tracks and playlists and find music which they would love to hear. So this is what makes the recommendation problems very, very important and challenging for us. Now, I'm just going to spend like 2-3 minutes on just giving a rush to view of what the past decade and like 2 decades of research and recommendation systems have focused on. And then using that background, I'm going to motivate some of the future work which we are doing right now. So like 10 years ago or more, like Netflix has this huge challenge on recommendations, movie recommendations, and some of the best performing models were collaborative filtering models. So the idea here was that if we can represent users and items as a matrix, then we can do matrix decomposition, and then using the user and item representations, we can go on and do some nearest neighbor search and find content to recommend to users. We then thought that, okay, instead of a matrix, I can extend it to a tensor. So then there's a lot of work around encoding the context with the user and items in a tensor and then doing tensor decompositions. So again, a lot of work has been gone around into creating tensors. The plot you see on the bottom right is a tensor matrix joint decomposition, which will give you vectors for users and items, and then you can kind of do some nearest neighbor on top of it. Latent variable models has been around for like almost 2 decades now. A lot of work in the recommendations community have gone into encoding their own business and industry intuitions around what makes a good recommendation, and then you can solve these latent variable models and kind of do recommendations. Now, interestingly, about like 10 years ago, a lot of recent interest in neural embeddings came up, and people started creating these user embeddings. They started adding side information to these embeddings as well. And eventually, they started learning these joint user and item representations. So there's a nice paper at Wisdom 27 doing this joint modeling of users and items for recommendations. Now, interestingly, right, I mean, we've seen collaborative filtering work well, we've seen embeddings work well. So the natural next step was to look at neural collaborative filtering. So some of this work tried to look at learning embeddings of users and items, but also doing some collaborative filtering layers in between in order to learn the final score which a user might give to a particular item. In general, not just these methods, but there's a lot of variations in the recommendation styles which people have researched. So some of these are like long and short-term representations. Some of it is like cold start recommendations or cohort-based representation. So in general, cohort-based could mean that maybe there's a new user and we don't know much about that user, but maybe we can relate that user to a group of users and then use that group's information to make our recommendations. People have done some work on multi-view and multi-interest models. So if you have a home device which is being used by more members of your family, then you might want to disentangle their interest and learn multi-interest models as well. So again, very, very interesting challenges lie over there, and a lot of work has gone into that. Recently, we are seeing multitask recommendations that not only I'm going to predict one task, but I'm going to predict multiple tasks together and do it for recommendations. So Google also has a very nice paper on YouTube at Rex's last year on multitask recommendations in production. So this is giving you a lot of flavor of the kind of different approaches people have looked at in recommendations community. But we asked the question, like, what do they all have in common? So the common thing they have is that they're all centric around the user needs. So it talks about user experiences, it talks about user engagement metrics. We're looking at developing user personalization models, looking at metrics which capture user dissatisfaction, user satisfaction, and all that. Now, this is great. I mean, there's a tutorial, recent one on user engagement, which talks a lot about this in great detail. But the thing is, we want to ask the question that, is caring about the user enough? Because as we go on and look at a lot of these like upcoming billion-dollar businesses, they're all multi-stakeholder platforms. So if you look at Uber, so Uber connects the drivers to the riders, right? So your user is the rider, but then like you also have to care about a lot of these Uber drivers as well. So on Airbnb, you have the guest and host. So again, like your optimization models and your machine learning models have to take into account the objectives, not only from the user side, but also from the other stakeholder side as well. So same for Etsy, same for eBay, same for Amazon, same for a lot of these logistics companies as well. And same for us for Spotify, that we want to do recommendations, keeping in mind not only the user needs, but also the artist needs as well. So this kind of creates a scenario that we care about recommendations as a multi-stakeholder problem, that we have user, but also we have other stakeholders like the artist, the drivers, or your host on Airbnb. You have your delivery partners on Uber Eats. You have the platform economics as well governing how you do your recommendations. Now, essentially what the background pitch over here is that we want to go from a user-centric system and develop a multi-stakeholder optimization system. So this is the premise of today's talk. So in the next 20-25 minutes, I'm going to talk to you about two parts. One is I'm just going to elaborate on a contextual bandit model, which is user-centric. And then I'm going to use that base to expand on and introduce multi-objective modeling in that bandit model to kind of make it multi-stakeholder. So yeah, let's spend like around 5 to 7 minutes on this problem and then like go on to the second one. So essentially, we're going to talk about user-centric bandits. And this is work which we published at Rexist in 2018, about a couple of years ago, and then we deployed this model in production. So you can refer to this paper for a lot of details for what I'm going to talk about next. Right. So the question is, if you look at the homepage, so the image you see is the homepage at Spotify. So if you look at the homepage, then you see that we have these shelves. So shelf is a rectangular entity, which is a rectangular box, and each shelf has a shelf name. Over here, marked as your heavy rotation. If you look below, it's like recently played or jump back in. And there's a card. So card is a playlist. So essentially, the way we look at the homepage is that we have a bunch of shelves, and each shelf has a bunch of cards. So essentially what it means is like, as a user, you get this grid of recommendations. So each item in this grid is a card, which is a playlist which we want to recommend to you. So now the question is, how do we do explore exploit over explanations? Now, if we look at explore exploit problem, then in general, a lot of work in the bandits community has developed methods wherein we can use some of these models to recommend content. So the basic premise over here is that I want to learn this policy, which will be the action selection policy, so the arm selection policy. So if you look at the bandit model, then it's similar to the slot machines in casinos. And the goal is that you pull an arm, and then you get some reward. So here, pulling an arm means like we select a playlist, which we show to the user, and the reward is whether the user likes that playlist or not. So here, the details of this include that we have a candidate set. So we have a list of candidate playlists, which we can pick from to recommend to you. We have a reward function, which decides how well the selection was made, and we have an exploration strategy. So this means like how much you want to explore or how much you want to exploit. So the explore exploit, just spending a second on this, would mean that there are certain things which I know the user likes a lot. So then I'm going to go into the exploitation mode and bank on my knowledge and show content which I know the user would love. Or at the same time, I might explore. So in exploration stage, I'll go and hunt for things which I don't know. I'm uncertain if the user would like it or not. Let's just try to show to the user and observe whether the user has a taste profile in this regard or not. So that's the explore exploit strategy. Now the question is, how do we do it on explanations? So if you look at the slide, then the way we recommend to you content on homepage is under explanations. So on the right, you might see like shows you might like or get cozy for autumn. So we've seen that explanations play a lot of important role in how users engage with these recommended content. Now, essentially, the problem becomes that if I pick up one explanation and I pick up each of these items, then these naive combination of each item for different explanation is an intractable problem. So naively, the bandit has to explore all different possible combinations of items and explanations and gather enough information on those before it's able to exploit the best combinations. Now, this is combinatorially very hard. So that's where we introduce this algorithm, which is BART. So BART is like a famous Simpsons character, and the homepage team at Spotify is a huge Simpsons fan. So we created our algorithm named BART as well. So BART stands for Bandits for Recommendations as Treatments. So essentially, it has like three main components. So the first is a user preference model. So user preference model could be anything which predicts whether a user is going to like this content or not. So it could be a factorization machine, it could be a high capacity neural network, any model of your choice could be used as a user preference model. We condition it on context. So context is anything we know about the user, about the item, about historic preferences, and so on. And because this is a contextual bandit model, so all our decisions are conditioned on context. We also have a training procedure. So again, like I can spend a lot of time on this, but unfortunately, we don't have much time to go into details. But counterfactual training involves some sort of like randomized data collection and training our models and evaluating our models via counterfactual estimators. So this is a very, very important topic across many industries. And it allows us to kind of get rid of the position bias, get rid of various other biases present in the data. And interestingly, we have a ranking procedure. So how do we create this stochastic explanation grid? So the grid I was showing about, like these horizontal rows of shells and then like ranking shells in the order. So let me spend a bit of time on like the ranking procedure. So in general, we make these assumptions of horizontal scrolling and vertical scrolling. So essentially what that means is that, remember, we want to learn that policy pi from which I can draw an action, from using which I can decide which card to pick, which playlist to pick and show to the user. So essentially in this user awareness, which is the real estate on your homepage, I can create one shelf at a time. So essentially I'll pick up one card and then show that card to the user. What I'm going to do next is I'm going to pick up another card and show that to the right of that card. And I can keep on doing that. So that would mean that I can create these shelves at a time. So these shelves would be a combination of a sequence of playlists horizontally. Now that we have these shelves, we can apply another bandit model on top of these created shelves as well. So essentially what that means is I'm going to pick up, using my action probabilities, one shelf and then show that to the user. And then I'll go on doing it vertically and create the entire homepage for you. So that's how we kind of decompose this problem and create, use these two-level bandits to create your homepage. Now, I mentioned that we have to train these models using reward functions. Now, how do we decide the reward for the bandit model? So the simplest thing we could do is have a very simple binarized reward that says that if the user streams the content we showed for t seconds, then that's great. I'm going to give it a +1. If not, I'm not going to give it. I'm going to give it a 0. Now, this is a very naive version of reward, right? Because across all users, across all content, you just have a single variable reward, which is a bit more naive. So here, what we did was we looked at variations across playlists. So some playlists are usually consumed a lot longer than other playlists, like sleep music playlist. Same for users. So there's a lot of variation across users. The jazz listeners consume jazz music more and other music more as well than the average user. So now if we have enough variations across users and playlists, then I don't want to create a single function for all users for all content. So this is where we kind of go into distribution-based rewards. So can I train and develop these reward functions which are cognizant of the user and cognizant of the playlist specifically? So we did this work and presented at the web conference paper in 2019, looking at distribution-aware rewards. So essentially the core idea is fairly simple, that you have users, you have playlists, and can we do co-clustering? Now doing co-clustering at this scale of 100 million plus users, that's the challenging part. So in the paper, we go into a bit more detail about that. But the core idea is that I can look at user clusters and playlist clusters, co-clusters together, and within each user and playlist co-cluster, I can then look at the distribution. Now that distribution could give me and help me define my reward function essentially. So essentially what that means is like, I don't have a global prescriptive reward function for all users, all content. I'm going to look at how this set of users interact with this set of playlists, and then using that distribution, define my reward functions. So what we did was we tried some of these models via different A/B tests, and it gave some decent results. And we then kind of deployed this model. And this is the BART model, which I was talking about. So the contextual bandit model, which was in production at Spotify close to back in like 2018, and still some version of it is already in production as well. So we got some amazing results in actual production metrics on using some of these techniques I was talking about. So that's the first part. So the takeaway messages so far is that naive combinations of items and explanations is combinatorially hard. And breaking up the problem into horizontal and vertical shells helps us make the problem tractable. Now, bandits allow us to explore, exploit, in addition to over-explainable content. A very important points, but which we haven't covered yet, are off-policy counterfactual evaluation. We have some work from our group published in recent conferences on this topic. I haven't much talked about the benefits of explanation and the various machine learning challenges which went into deploying it at scale. So again, a lot of this is covered in some of these papers which our group has published in the last couple of years. But taking a step back, so this serves as a base model on which we can now bring in a multi-objective flavor. So now we have looked at a single objective bandit model, and let's try to go from a user-centric world to a multi-stakeholder world. So here, I already showed this slide before, that maybe instead of just caring about user, I should be mindful of the other stakeholders on the platform as well. And essentially the goal would be that, can I create a multi-objective model to kind of satisfy the different objectives different stakeholders might have? So let's look at what would that look like, I mean, from a bird's eye view. So if I just care about user-centric objectives, then I have a single objective function, which is a user-centric function. And essentially, like, I'm just optimizing that function for my recommendations. But now, because we care about the suppliers, we care about the platform economics, so now I should kind of mature towards a multi-objective function. So let's take baby steps, right? I mean, let's not jump, take big steps. Let's just go from a single objective model to just 2 objective and look what it looks like. So we have this paper at SICM 2018, which is talking about fair marketplace and how do we trade off user relevance and supplier diversity. So essentially, if you take 2 stakeholders, the user and the supplier, so we can have the objective of relevance to the user. We want to recommend content which is relevant to the users. And we can look at exposure diversity, that how many of my suppliers am I exposing? Am I being like very, very naive and only picking up a very small subset of suppliers? Or am I being a bit more equitable and picking up suppliers from across the popularity spectrum? So I don't want to be biased towards the head of the distribution. I want to be a bit more equitable towards the suppliers I expose. So if you're on Amazon, if you're Airbnb, or even if you are like the Uber Eats platform, then you want to recommend restaurants which are different restaurants. You don't want a single restaurant to get all the delivery orders. You want a fair amount of distribution across different restaurants there. So if you look at one quick example, then on this plot, we plot the diversity estimate on the x-axis. So that means things on the right would mean that we are recommending many, many artists. And things on the left would mean that we are recommending very few artists. On the y-axis is relevance. So how relevant was the recommendation to user? So importantly, we see that on the top right, we have very, very few sets. So that means there is nothing which is highly diverse for suppliers and highly relevant, because had it been there, then the problem is solved. But here we see that we're starting to get this feel that there is a trade-off decision here. So the question becomes, how do we trade off between user relevance and supplier exposure? So we looked at a bunch of optimization policies for recommendations, wherein you can go from some simple approaches like, I only care about relevance, I only care about supplier exposure. So you can have these like argmax policies, which are very simple, greedy optimization routines. You can look at policies 3, 4, and 5, which are starting to do this trade-off. So a probabilistic policy might make probabilistic decisions that with certain probability, I'm going to focus on the user. With certain probability, I'm going to focus on the supplier. The policy 5 is a guaranteed relevance, which is a very intuitive policy, which says that often when we talk to product owners and product managers, they would be of the opinion that, hey, I don't want you to degrade relevance on my product. So perhaps what we can do is we can guarantee that you're not going to go beyond 0.8 relevance, let's say. And once I have that guarantee, then let me do whatever I want with the other objectives. So you can have a constraint optimization setup and kind of guarantee that we're not going to tank relevance beyond a certain extent and then kind of optimize for other metrics. We also had a couple of adaptive policies which take into account user adaptiveness. So how okay is the user with diverse content? And if they're okay, then we'll recommend that. If not, then we'll go back to relevant content. So again, the takeaway message is the paper has a lot more details on these problems, on these policies and evaluation. But one of the interesting takeaway messages here was that we see a good inflection point here, that there is a nice curve trade-off, which gives me enough gains on diversity of suppliers without hurting user satisfaction, without hurting my relevance by much. So this is great. That means like I want to look out for these optimal policies and optimal points and then stay within that region in the Pareto optimal curve, perhaps. Now, the problem is this was easier done in a 2-objective setting. The moment we have multiple objectives, it becomes fairly complex to solve. And this is exactly what the next few slides are going to motivate. So here we looked at, let's say, 3 objectives, like user satisfaction. And for user satisfaction, you have 3 different objectives, like stream time, clicks, and number of items consumed. You can look at diversity. You can also look at promotion. So I can select a subset of underserved suppliers on my platform and try to promote them more. So if you look at it, then, so yeah, on the right is a heat map of the correlation between these objectives. So again, different SAT metrics are correlated. The diversity is neutral, and the promotional objectives really starts to hurt these satisfaction objectives. So SAT is an abbreviation for satisfaction. So now I know that if I just optimize for one satisfaction objective, that's great. I'm going to get the others kind of for free. But if I care about diversity, then I have to explicitly optimize for it. And the moment I add a competing objective, it becomes a lot harder to solve. So this is exactly what we kind of addressed. And we had a paper at KDD this year, which is looking at a multi-objective contextual bandit model. So the goal is, I kind of referred back to the slide, that we have multiple stakeholders, and I want to have a function which considers and respects all of my stakeholder objectives. So what we did was we went back to a function which is fairly well studied in the economics community, which is the Gini function. So then we formulated our bandit problem around a generalized Gini function. So essentially, this function says it's a special form of OWA. So OWA is an ordered weighted averaging. So it kind of preserves impartiality with respect to the individual criteria. So what I can do is I can apply this Gini function on top of my different objectives, and then the algorithm prefers allocations which are a bit more equitable across the different stakeholder objectives. So let me give you a bit more deep dive into what's happening here. So essentially, the goal is to find an arm selection strategy, right? Because the arm selection strategy says that which arm should I select, which playlist should I select and show to the user. Now, for a bandit instance at round T, we observe the features. So all these features are the contextual features you have about the user and item. Now, if we choose an arm K, which is if I select a playlist K, then we can observe a linear reward. But the problem is like in this problem, because it's a multi-objective problem, then my reward function is not linear, because it's a vector of reward. If I have 5 objectives, then I should look at some 5 rewards as well. So now the thing is, had I known what the mean feedback for each arm, for each of the objective is, then that's an easy problem. I can just do a full parameter sweep and then pick up the best arm, best playlist and show that. But because the rewards are conditioned on context, so a user may like the playlist in the morning, but may hate the playlist in the evening. So a lot of the times the reward is a function of context as well, and that's the contextual bandit problem. So now I cannot do a full parameter sweep, and instead I can go and optimize a multi-objective function. And this is exactly the function which I was talking about. So now what we can do is we can maximize this Gini index function and then pick up the arms essentially. So what that might look like is that, first of all, we set up some number of parameters like the number of arms, which is the number of playlist. We can define the number of objectives and some regularization terms. I can start with a uniform strategy that I have a 1/k probability of selecting each arm at a time. So I start with a uniform policy across all my playlists. And then what I do is at each round, I observe the context. So I observe the K context features. I estimate the reward. So I have trained some least squares regression, rich regression problems to predict what the reward would be. And then I kind of use that to inform the action probabilities. Now there's a projection step involved because you have a fixed set of candidates and you have to kind of make your action probabilities map back to the action space you have. So essentially, once you do that, you can select an arm based on these updated probabilities and then sample an arm. So sample an arm means that you decide which playlist should I pick and recommend to users. And essentially, once you do that recommendation, then you observe the reward for the different objectives, and then you can go back and update your models. So that's what's going on. So now what we've done is we've looked at a single objective bandit model, and then we've tried to add in a Gini function optimization, which optimizes for a multi-objective formulation. And it gave us some very, very interesting results. So if I just look at, let's say, user-centric optimization, so if I don't care about other stakeholders on the platform, if I just do a multi-objective formulation on only user-centric objectives, like clicks, like number of streams you have, the total number of songs you played, then we observe that the multi-objective model performs much better. So on the plot on the right, the yellow curves are the proposed multi-objective bandit model. And now we see very, very interesting results that optimizing for multiple interaction metrics performs better for each metric than directly optimizing that metric itself. Now, this is a very interesting result because if I want more clicks, then not only should I only optimize for clicks, I should optimize for clicks, total number of items consumed, and so on. Now, this means that the model is now being able to leverage this rich structure between these objectives itself. So if you look at the metrics, right, if you look at these objectives, then you have to have a click in order to have a 1 minute session. You have to have many 1 minute sessions in order to have a long 5-hour duration session as well. So again, like there's often a lot of this like latent structures between these objectives, which now the model can learn and benefit from essentially. So yeah, so we saw that. Now let's say if we add in a competing objective. So I want to kind of expose some gender of artists. So let's say I pick up a subset of artists and I want to expose them more. So now this is like not a user-centric objective, right? So now we're starting to see that we can get significant gains in this objective without hurting user objectives. Now this is interesting because this means that it need not be a zero-sum game, that perhaps we can get gains in the business objective without hurting users much or without hurting users at all. Now this is very important, right? Because as a platform, you can now kind of strive to get and create algorithms which give you benefit to your other stakeholders without hurting users at all. So there is a world wherein like everybody benefits and you kind of go home happy. Now, we tried some other approaches of multi-objective and they don't perform as well. So again, a very obvious takeaway is like, just the fact that you are doing multi-objective is not really that great. I mean, you have to do the right multi-objective in order to kind of get these wins. So that's the takeaway from the second part. And hopefully I've convinced you that in general, there is an interplay between these objectives, and multi-objective bandits are useful. But in general, as a business takeaway, as an industrial researcher, it's worth thinking that it need not be a zero-sum game. Perhaps you can benefit all your stakeholders at once. A couple of things which we have not covered are two-stage rankings and objective balancing techniques, which is something which we have kind of recently worked on and deployed as part of the radio model at Spotify. Just a quick plug-in for some other work, which I'm not going to talk about in detail, just a slide which you can go back and look at the paper, which is going to get published at Wisdom 2021. So here we are looking at diversity, content diversity. So if you look at consumption patterns on your platform, then diversity is an enabler for consumption shifting. So what that means is like, if some users want diverse content, then maybe I can try to pick up some artists or some suppliers on your platform who want to get exposed more. And then there are users who want to listen to diverse music as well. So that would be a match, a perfect Lego style match, right? That there are users who want more diversity. And then in terms of my consumption distribution on the platform, I want to shift it towards a more equitable consumption perhaps. So then we can kind of match this using some reinforcement learning techniques and kind of get benefit of both, like benefiting the users who want diversity and also suppliers who want to get more exposed on the platform as well. So again, like there's a paper which you've written, it's just got accepted, and we kind of in future kind of be happy to talk about this in detail. But essentially, like the takeaway message is that we can look at single objective models, we can look at multi-stakeholder models, but essentially a lot of these platforms are starting to now think about a whole ecosystem, right? So we are creating this platform ecosystem, which is looking at users, suppliers, and platform, and developing these algorithmic balancing techniques to kind of find and show content to the users at scale. So finally, if you're interested in this topic, you can look at the KDD tutorial we gave on this topic. And also, like Spotify has been very generous in like public dataset releases. We have a dataset from 2 years ago, which is a 1 million user created playlist. We recently released this sequential dataset of 1 million user sessions, and that has important feedback information from users as well in an anonymized fashion. So you can do a lot of session level modeling, sequential recommendations on that dataset. And finally, some of the teams internally have released with Trek a podcast dataset, so 100,000 podcasts and transcripts of those podcasts as well for academic researchers to do research on. So that's it from me. I hope you enjoyed the talk, and I hope you like the multi-stakeholder notion of recommendations.
Thanks a lot, Rishabh. That was really insightful. I mean, it's especially interesting for all the enthusiasts that we do have some data sets which we can play with. So maybe now let me just ask Ramansh to take over and ask what questions he has got for you. If you could just stop. Yeah, thank you so much. Maybe Ramansh, you could take over.
Yes. Thank you so much for the highly informative session, Rishabh. We do have many questions, but I would like to ask this interesting one. As a product engineer, how would you say we make good recommender models, systems for our users based on personalization, all the while addressing data privacy issues?
Yeah, so that's a great question. A bit unrelated to my specific current work at Spotify, but in general, like we do have machine learning. Okay, thankfully, the industry and the research community is starting to make progress on federated learning, right? So essentially, like there are topics and there are machine learning models which perhaps don't need access to your data and don't need to be trained in a centralized fashion. So a lot of these companies might have centralized data repositories which have access to all user data. So essentially a lot of the, I mean, if you look at NeurIPS right now, as we speak, there's a lot of papers getting discussed on federated learning, on how you can train your models in a decentralized way, that they don't need access to that critical, crucial, private health data to train your models. You can just go and access only some of these shared attributes of the data and train your models at scale. So I think, like, interestingly, we live in a duration when a lot of progress has been made on differential privacy, on federated learning, on decentralized training of our models, that perhaps you don't need to have access to that large scale data across users, and you can train a lot of your models in a privacy aware manner. So yeah, I mean, federated learning is the right topic to kind of dig deep into in that domain.
That makes sense. Thank you so much for explaining on that specific issue. So at this point, I would once more would like to remind our attendees to head over to our Slido platform if you have any more questions to ask us. And at this point, I would thank you so much, Rishabh, and I would like to invite Griven to start our next session. So Griven, please.
All right, so next on deck we have Arnu. Arnu will be taking us through the next round of discussions on his research papers. So Arnu is a research scientist and team lead at Instadeep Limited. And he also broke grounds as the first African-based AI researcher to have 2 of his papers accepted at the NeurIPS Conference. Arnu has a wealth of over 1 year as a research scientist. He also has a computer science Ph.D. from Stanford. And Arnu has got a keen interest in communities and was once an organizer for deep learning in Daba X, Western Cape, South of Africa. Interestingly, Andrew, for the love of music, has started to learn strings on how to play drums. And alongside his wife, they read bedtime stories to their dogs. So Andrew, at this point, I'd like you to take over and carry on.
Okay, thank you so much, Griffin. Thanks for the introduction. Just going to share my screen. Can you hear me well?
Yes, we can, yeah.
Okay, and you can see my slides?
Yep, it's visible.
Okay. Yeah, first of all, I just want to thank you so much for the invitation. It's a real honor to be a speaker here. Super humbled by the amazing list of speakers who are here, and I've definitely enjoyed it a lot and learned a lot. The panel discussion was amazing. The talk just now was really nice. I use Spotify every day, so it was cool to hear how things are being recommended. Yeah, and I also had the privilege to actually go to Nairobi last year for the deep learning in Daba, and it's just an amazing place. The people are so friendly, and really had a great time there. So yeah, this talk is title is Common Pool Resource Management using multi-agent reinforcement learning. And it's just going to be a bit about some ideas around multi-agent systems, and also just touch a bit upon the research that we did at Instadeep this year. So I guess the first question really to answer is maybe why we consider multi-agent systems. And I want to start kind of just by showing this paper. So last year there was this big paper that was published called Tackling Climate Change with Machine Learning, and it was a really sort of long, extensive paper showing all the possibilities that can be harnessed for machine learning to kind of make a change in this really, really important problem facing humanity at the moment. And it has some really notable authors like Andrew and Demis from DeepMind, Yoshua Bengio, and includes various really influential AI companies and universities. And for anyone who's interested in this problem, it's not just in terms of helping the world or maybe making a difference, but this paper also highlights lots of entrepreneurial opportunities. So there's also sort of for the business minded, maybe to check it out. But just in terms of for this talk, they highlight a lot of different areas that might be applicable, where machine learning could sort of make a difference and also be useful in terms of maybe starting a business or just launching some influential applications. So you have things like electricity systems and transportation, buildings and cities. And within each, you have things like reducing waste in supply chains and enhanced precision agriculture. And I think many of these cases, if you look at them, you can find that they sort of fit well into multi-agent learning systems. So the system that is being deployed might have multiple sort of decision makers that need to kind of try and optimize some perhaps joint reward or objective function, and then really try and cooperate to come to some solution that can work well. But a different sort of motivation, or an additional motivation for perhaps why multi-agent learning systems could be very useful is this idea from a paper that was published last year by DeepMind. And it sort of talks about the emergence of innovation through multi-agent learning. And they put forward this hypothesis called the autocurriculum hypothesis. So I'm just going to read it here. It says the dynamics arising from competition and cooperation in multi-agent systems provide a naturally emergent curriculum, where the solution to one task often leads to new tasks, continually generating novel challenges and thereby promoting innovation within the system. So perhaps just as an example, there's if you consider this picture on the left here, you might have some multi-agent system that interacts, and it itself consists of subcomponents which themselves interact. And what could be happening at each and every level, if you condense it down to the idea of just two players interacting. So we have this row player here that has two strategies. So it could either deploy a strategy A or strategy B. And similarly, column player can choose among two strategies, A and B. And what's interesting is that if the row player is just deciding to play strategy A, the column player might find itself on sort of a objective landscape or loss function of some kind that is fairly flat in the region in terms of its strategic choices, whether it decides to play A or it decides to play B, and might then be indifferent in terms of the payoffs it could get, for example. But if the row player decides to play strategy B, then suddenly the landscape could completely change. And now that presents a challenge to the column player. And the column player needs to sort of innovate and figure out which strategy might be the most sort of the best strategy it can decide to play in corresponding to the row player's decision to play strategy B. And then there's a difference that arises based on the shape of this landscape. So there's some work that actually showcase this to kind of emerge in a reinforcement learning setting. So this is some work by OpenAI. It was published this year on the emergent tool use for like multi-agent game. So this game is hide and seek, and you have these hiders in blue, two agents, and you have these seekers in red. And just like when you're young and you're playing hide and seek, the hiders get a few seconds to start. So the seekers are counting a bit, and the hiders can decide where will they hide, what will they do, and then the game starts, and the hiders try and the seekers try and find the hiders. So in the beginning of training, the actions are just random of all the agents. And then the first strategy to emerge is chasing. So these seekers will chase the hiders, and the hiders will figure out that it's in their best interest to try and run away. But then as this new challenge is presented, the hiders figure out that, well, they can actually use these boxes and they can move them to these entrances and lock them. And once they've locked them, the seekers can't really enter this room. And so presented with the previous challenge, the hiders kind of learn to innovate and have a new strategy that they've developed. But once this strategy is now in motion, in action, the seekers figure out that they have access to this ramp. And so eventually through learning, they learn to move this ramp, and that means they can have access to the room. And now again, they can get some reward by tagging the hiders. And then finally, the ramp defense strategy emerges as a sort of response to the challenge. By in the beginning of the game, when there's a few seconds, the hiders can actually move out of this room, grab the ramp first, move it inside, and then lock the boxes, and then they're safe throughout the game. So it's just a really sort of interesting kind of display of how this idea of an auto curriculum can kind of promote innovation throughout learning. But I just want to take a moment to perhaps like pause on this idea of learned systems. So if we think about maybe using multi-agent systems to solve tasks and their learning, there's just a few things that we might consider. So these systems learn by interacting in a dynamically changing environment. And if we consider to use them for something like safety critical operations or managing crucial life supporting resources, then it becomes quite important that we try and understand sort of the underlying mechanisms that's driving their behavior and the interactions between agents in these systems. So this brings us to some of the work that we did this year. So this is joint work with lots of different authors and researchers. So we had great interns who helped on this work, Scott Cameron, who's now at Oxford, Ilan van Bouillon from Stellenbosch University, Tom McKing from University of Cape Town, and Shahil, who's from Wits University in Johannesburg, the Rail Lab. And I just want to give a shout out here to the Deep Learning Indaba for making things like this possible. We met through the Indabas and it has really created a beautiful environment and family to kind of find collaborators. And I think we should keep pushing so that we have collaboration, not just over universities in the country, but also across different borders and different countries. So we considered common pool resources as a sort of important area to look at in terms of what could be useful in terms of using multi-agent systems, but also crucial areas where you might want to make sure that you understand what's going on. And I hope through the talk it might become clearer why this is the case. So a common pool resource is a resource where basically exclusion from access is difficult or impossible. And if a single agent takes from the resource, it diminishes what's available to the rest of the agents, at least for a certain time period. So these resources might be regenerative, and so the resource could regenerate, but at least for the time being, there's less available for everyone else. And examples of these include lots of different important resources that are crucial for humanity, like arable land, fresh water, forest, atmosphere, and even the climate. So you can think of sort of the unpolluted space or carbon-free space as sort of like a common pool resource. But these resources are susceptible to something called the social dilemma. So this is when a conflict between sort of short-term individual and long-term collective interests can lead to suboptimal outcomes. So there's this graphic on the right that's depicting what's called the tragedy of the commons, which is a typical social dilemma, where you have someone who have two different people having access to water, and the one person says water belongs to anyone, I take as much as I want, and the other person says seems there's less and less these days. So maybe one of them has a more sustainable mindset, taking just what they need every day, and the other person realizing that it's a common pool resource and they can't be excluded. It's in their best interest to just take as much as they want. But if everyone would adopt that mindset, then the resource would run out, and in the long run, everyone is worse off. And this is called the tragedy of the commons. So our research question was essentially along the following lines. There's evidence that human institutions or a collection of humans seen as rational agents trying to manage a common pool resource can lead to these social dilemmas. And we were particularly interested in knowing whether if you have a multi-agent RL system, something that could learn through reinforcement learning, so maximizing some joint reward function between agents, and in the setting of common pool resource management, whether they would also be susceptible to succumbing to social dilemmas, or can you escape these situations? So we considered this simplified water management system. So we built this environment where you have control components as your agents, these shuttle valves, and the agents have actions where they can open and close these valves, and they essentially get reward for how much water they can provide to their respective societies. To analyze the system, we considered game theory, and in the classical case, so game theory is sort of mathematical formulation for analyzing strategies between players and incentives and equilibrium points. And the classic example when introducing game theory is called the prisoner's dilemma. So in this case, the story goes that you have two people who just got caught for some crime and they're being interrogated, and they have an option to confess to the authorities, or they can keep quiet. And often game theory is kind of presented as this matrix where, again, you have a role player that can choose cooperate, which in this case is confess, so cooperate with the authorities, or defect, which is keeping quiet. And the same with the other partner in crime, the column player has the same strategies. And here these payoffs mean higher is better, but you can think of in terms of negative payoffs as the number of years you would spend in jail. So just as an example, if they both cooperate, as in they both confess to the, keep quiet, then they will get this payoff. If they both confess, they will get this payoff. And if the one confesses and the other one cooperates, then they would receive this payoff. So I just want to make sure that we understand. So in cooperate, both cooperating in this case is confess, is keeping quiet, and defecting is confessing. And if you each player can then sort of do the other player in by confessing when the other player does not, and then they would go free, essentially get a really high payoff, and the other player would get a low payoff. And what makes this game special is that you can analyze the different strategies and find that there are what's called dominating strategies. So in the case where you fix the column player's strategic action to be cooperate, the row player has the incentive to defect. So in a sense, to confess and get a higher payoff of 5. If you fix the row player, the column player's strategy at defect, again, the incentive is to defect and confess as well. And the same is true for the row player versus the column player in the fact that the payoffs are symmetric. And when you done this analysis, you realize that the dominant strategy for both players is to defect, and that gives you this Nash equilibrium, which is where both players are defecting. But what is interesting about this is that the equilibrium point for this game is actually a scenario where the payoffs for each player are actually lower than they would have been if both players cooperated. And you can actually define social dilemma. So social dilemma is specifically when you have these 3 conditions. So full system cooperation is preferred to full defection. So that means this point is preferred to everyone defecting. Full system cooperation is preferred to being exploited. So from the row player's perspective, getting 3 is better than getting 0. And the third condition is for a certain strategies that you can play, there is some incentive to defect. So here there's incentive for the column player to move to defect, and same for the row player here to defect. And if these three conditions are satisfied, then you have what's called the social dilemma. But these matrix games are quite simple, and game theory as sort of like mathematical formulation for studying these type of games are hard to extend to something like multi-agent reinforcement learning, where you have multi-step interaction and full policies that are being learned. And so the problem is, if you have this, the underlying agent incentives in these complex learned systems are quite difficult to analyze. So we need something else. And for this, we turn to what's called empirical game theoretic analysis. And here the idea is fairly simple, but it has sort of multiple stages. So one thing you could do is you could essentially manipulate your environment in such a way that you can expect certain behavior to be learned, certain policies to emerge. And once you can kind of predict what behavior would emerge under certain conditions, you can then label these learned policies as either being cooperative or being policies that are associated with defecting agents. And then when you play out these different policies sampled in different combinations, you can then evaluate or estimate sort of the payoffs in a meta level game that is this matrix. So you have two cooperating policies, you evaluate how they would interact in the environment, what expected reward they would get, and then this way you can estimate what you would find in terms of like a matrix game payoff. And I'll discuss just how we did it in our case in a second. And when you do this, there's this new categorization or maybe sort of solution concepts that if you think of Markov games in its entirety, within that you find sequential Markov games, which is where you'd have the mathematical formalisms of multi-agent reinforcement learning. And then if you can map a sequential Markov game using this empirical game theoretic analysis to a Markov game social dilemma, so something like the prisoner's dilemma, then this is classified as a sequential social dilemma. So in our case, this is exactly what we tried to do. So we had this water treatment plant example of a system, and what we could do is we could say, let's have high regeneration rates of the water in the treatment plant. So in this case, if you have agents, they would learn policies that can just always take, because the regeneration rate is high enough that there's unlimited kind of water for everyone, and they can send that to their respective sector. But if you then transport these policies that are essentially completely greedy into a normal setting where the regeneration rate might be something that is more realistic, then these policies can be seen as defecting agents that just want to take all the time and haven't learned any form of restraint. And the opposite case is where we can have low regeneration rates and then learn policies that are more sort of sustainable in the long run, has learned that it's best to take sometimes and cooperate in terms of how to take, and then label these as cooperating policies. So in our case, because we have 4 agents, we had to do what's called a shelling analysis. So instead of having a matrix, we now have our results in this form. So on the x-axis, you have the number of cooperators in the system. So for each case here, if there's 1 cooperator, it means there were 3 defectors. Here is full defection, and in this case, it's full cooperation. And this red line shows the average payoff for a defecting agent. This green line, the average payoff for a cooperating agent, and then this is the sort of average payoff for the group as a whole. These lines here represent the conditions that we were talking about. So full cooperation is preferred to full defection, and as well the second condition and the third incentive to defect. And this point here represents the equilibrium. So if you would take, for example, this configuration over here, you have 3 agents cooperating, 1 defecting. there's the incentive for the cooperating agent in this case to defect, because it will then move to this configuration of 2 defecting and 2 cooperating agents, with the defector getting a higher payoff. And similarly, there's still incentive here to keep moving to defection. But once here, there's no incentive anymore to move away from defecting or cooperating, because there is less of a payoff. And similarly with the cooperating agent, to move to defection is a lower payoff, and moving to further cooperation as well. So the research question here that we kind of had, if we can just revisit it quickly, is to essentially say, okay, if we have agent systems where social dilemmas can exist, but these depend on the payoffs and the policies, these ultimately depend on sort of information structures. So if you think of humans as their ability to act as rational agents, then our ability is given in some sense as evolved cognition. But if we have a multi-agent RL system, we can do system design, and we can choose the information structures that we use. And the question is, how does this affect whether we actually find something like a sequential social dilemma emerging? So we considered 2 broad multi-agent RL camps of algorithms. So these are sort of considered state-of-the-art currently. And the first is in terms of direct information sharing. So you have algorithms that share observations or policy information. And the second was a class of algorithms that did learned communication. So you have different strategies for learning communication protocols, and maybe you have sort of like a meta network controlling the different agents with differentiable connections between them. And then these agents can learn sort of abstract representations of communication. So our findings was the following. We definitely found distinct behavior between the different algorithms, specifically along the higher categories of whether algorithms communicated with learned communication or direct information sharing. And here is just a heat map where on the x-axis we have regeneration rates from high to low. And here are the different algorithms that we considered. For direct information sharing, as the regeneration rate became less and less, so there's less of the resource, the agents had to kind of adopt a higher percentage of restraint. And for the communicating algorithms, this seemed to happen at a far lower regeneration rate. And our hypothesis for this is something along the lines that the learned communication can help coordination. So if you have better coordination, then you can maybe have more sustainable sort of resource extraction. But the interesting thing is at very, very low rates, these algorithms seem to go back to being greedy, showing less restraint. And this might be sort of like a manifestation of the tragedy of the commons, where agents just realize their best strategy is to just take as quickly as they can before the resource depletes. So here we just had a plot of a sustainability metric. So it's essentially measuring how far into the episode agent is still gathering reward. So showing how long the resource can be sustained. And indeed, the communicating algorithms had far more sort of sustainability in terms of the way they extracted from the resource, except this interesting case of network A2C with some high variance. However, most algorithms actually found themselves to be SSDs or sequential social dilemmas. So we had these indicators that would show the social dilemma conditions being satisfied if these values were on the right here, so positive. And most of the algorithms we tested actually showed that they would be susceptible to finding suboptimal or inefficient equilibria if used in this case. And so here is a algorithm with direct information sharing, and the equilibrium point is over here, where for the group as a whole, it would be a lower average payoff than it would be if everyone was cooperating. But even if the payoff is maybe not bad in terms of the group as a whole, you might have, if you think of distributing water to different communities, you might have situations where the inequality between payoffs is something that could be that is undesirable. So here, for example, you have some defecting agent really exploiting the three cooperators here that are working together. And then finally, we found that the newly proposed Neurocom algorithm that was published this year was actually, under certain conditions, able to find a stable equilibrium point where all the agents were cooperating. And there was no point where there's an incentive to defect. So in any condition, the optimal strategy would be for the group to cooperate. So just in conclusion, we considered common pool resources and entertained the idea of maybe having these resources being managed using sort of like adaptable multi-agent systems, and considered multi-agent reinforcement learning as a particular case that could have great potential in this area. However, we must be mindful and make sure these systems are safe and that we understand what they do. And this led us to trying to investigate sort of some notions of interpretability in these systems. And our question was that can multi-agent RL avoid SSDs, so these social dilemma situations? And the answer was basically not always. It depends on the information structures that they use. So yeah, that's my talk. Thank you very much. We should take questions.
Thank you so much, Arnu. At this point, I think we'll have now questions over from Ramash's side.
Yes.
Ramash.
Thank you so much, Kevin, and thank you so much, Arnu, for the highly impactful and discussion and presentation about reinforcement learning. I found this interesting question that I would like to ask you on behalf of the participant. To African AI researchers and AI researchers in general, I would say, who are working to publish their work at top AI conferences and journal, what advice would you give to them or tips to address difficulties in polishing ideas, conducting experiments, and writing their paper?
Wow, okay, that's a great question. I think the first thing maybe to say is just like I really like the panel discussion where there was mentioned on believing in yourself and having confidence, and I think like first of all that's a big thing. What in my own case, what happened to me is when I started my PhD, I was actually at the first deep learning in Diab, and I saw a poster at the session there, and the person who was presenting there was from Wits University, and they published their work at ICML, and I was just blown away. I thought, this is how can this happen? We're not supposed to reach for these goals or something, and that really changed the way I thought about, and I thought maybe we should just believe and push and see what happens. So I think the first thing would just be like really, try to develop a mindset where you think, I can definitely do this, and if I put in the hard work and the time and things, I can reach a level where I can be with the top in the world and try and contribute to humanity in terms of the knowledge that we do have. In terms of like more practical advice for polishing ideas and experiments and writing papers and things, I think a very practical way to go about it is maybe find a paper that you really like. You've read it and it reads well, and the experiments are well done, and it just explains things well. And even the structure of the often papers are thought of as stories. So you're trying to tell a story. You're telling a story from why is the problem interesting, to why should you care, to what's the problem, how people before you tackled it, and then how you can maybe how your proposal helped or improved the state of the art. And I think if you take that paper and you really just analyze it and try and internalize the way it was written, or just sort of see if you're writing your own work or you're trying to come up with ideas or these type of things, to essentially adapt the mindset that you can try and emulate your favorite authors or things that they are looking at, areas that they do research in, and how they present their work. So I think that's one area to like, I found that really helpful. Like, I have a few researchers that I really admire, and when I read their papers, when I think of experiments that I would like to do or how I would like to write something, it's really helped me quite a bit just to think, like, how would they do it or how would they go about it. So I think maybe that's a good way to start. And then just ideas in general, idea generation, reading widely, I think is really great. Don't just read in your area of interest, read kind of a bit wider than that, delve in some other areas that might seem unrelated, but very often you'll see there's a big web that's connecting everything, and you find some really nice ideas.
That's very insightful advice to all the researchers, especially the ones that are especially getting started and they're dreaming big, that it's possible when you take it one step at a time and you work towards it, you will really work towards it. Thank you so much, Arnu, for your amazing presentation. It was really informative, and for answering that question. It was a great event today, and at this point, I would like to invite our chair of the meetup, Kennedy Wangari, to present the closing notes towards the meetup.
Thank you so much. Thanks.
Thank you so much.
Great. We've had a great event session. And as we get to Ramash, you can have the slides back. Yes. We've come to the end of the NeurIPS 2020 Nairobi Meetup. It's been a great session whereby we've been able to create an additional way to be part of this global conversation. We've had a highly impactful session. We've learned a lot. We've engaged. We've learned a lot from our speakers. And it's been a highly impactful session. We've also had great interactions with our attendees. We've also interacted with our organizers, our session moderators, our speakers and attendees. We would like to take this time to greatly thank you for making this event session a huge success and a worthwhile. And we say that special thanks to everyone, to our speakers, the 9 speakers, to our hosts, to our amazing and highly interactive attendees. Thank you so much. And just a few updates as we get to wind up. Within the course of this week, we will all get to receive a follow-up email with details to fill up a short survey. And these will be coming from deeplearning.ai. Kindly do provide your feedback about how this meetup was. Did we manage to meet your learning objectives and what you expected to learn? And this is going to help us so that we're able to improve on moving forward and our future activities, because we're looking at coming up in 2021, we have post NeurIPS activities that are scheduled and that we're going to communicate, and getting to hear from you the feedback and what you think we can improve on and what you think maybe we would need to allocate more time. Please let us know through that follow-up email that will be coming from deeplearning.ai. And also having filled that survey form, you'll be able to receive a separate email from deeplearning.ai, and this email you should be able to receive guidelines on how to redeem coupon codes for the deeplearning.ai courses. We'll also be having our speakers gaining access to any courses of their choice from deeplearning.ai that are hosted at Coursera. And lastly, we'll be all receiving a second email. This will be coming from the organizing team, and we'll be sending out this email that will have a link to access a full recap article of this event, the summaries and the key takeaways. So be on the lookout for the blog post and also the proceeding of this event. And also we'll be able to share a slide resources, the materials that were shared with our speakers, and any other vital information that our speakers did mention. And maybe you're not able to put it down. We shall also be able to be sharing that in the coming in the email that we'll be sending out. And also in that email, we shall also be providing an access link so that we're all able to have access to what the main NeurIPS conference has been discussing. Today is last day we're having the main program activities. So in that email, we'll be able to have a link to access the main conference tutorials, keynote presentations, and various workshops. And again, don't forget to check out the recording of this meetup session and more data science and machine learning content that is always posted on this YouTube channel. And with that said and done, thank you so much to our speakers, to our hosts, to our amazing attendees. Until next time, stay tuned. We have post NeurIPS activities lined up and coming. So be on the lookout, and we got a lot lined up for each and every one of us. Thank you so much.